and it's great to see so many here. So welcome from our part also. So I'm Monika, and this is my colleague Tekla. And yes, so before we go to our interesting program today, we want to say a few words about the FinnCERES flagship. So it started in 2018, and we are redefining bioeconomy by harnessing the inherent properties of lignocellulosics and developing advanced bio-based materials. And it's a collaboration between Aalto University and VTT, and combining our strengths. And actually we are going to the end. We just have one year left of the flagship, and the research we are doing, it's based on the foundation of fundamentals, so we do a lot of study interactions and advanced characterizations. Then we have 4 application-based themes that are solid foundation for future biorefineries, developing, for example, lignin valorization or novel fractionation technologies, clean air and water, lignocellulosics beyond plastics, and electronics, optics, energy, and energy application, showing what all you can actually do with the lignocellulosics that you might not have thought about before.
Thank you, Monika, and also warm welcome also from my behalf. And one, I would say, very crucial thing when we are thinking about these flagships is that we actually need to generate impact. And our impact is really based on the scientific excellence. And I would say that so far the achievements related to the science behind future bio-based materials, we have listed few very, I would say, turning points here, where we have been looking at this utilization of inherent properties of lignocellulose, which means that we are actually trying to take advantage of all what lignocellulosic building blocks can provide. And there the water interactions play really a crucial role, and turning that from plant cell wall actions towards materials engineering is one of the key features here. We have also been looking at the new initiatives for novel solutions for packaging. We have been able to demonstrate how nanocellulosics and cellulosic materials are able to capture microplastic particles. And I would say one of these, very revolutionary approaches have been utilizing the light and light transportation and light management in lignocellulosic-based systems. And there we have been demonstrating the utilization of lignocellulose in photonics and also other optical applications. And as mentioned, the impact is really crucial thing, and also why the flagship status is very important, and how to gain the flagship status is that we need to look at the I would say the industry and companies crucial for Finnish society and Finnish economy. And there we can come up with quite quick conclusion that yes, the forest-based materials, forest industry is really crucial, and we should find ways, novel avenues also to make sure that the industry is also benefiting from our key findings, what we have been able to generate in the frame of the flagship. Here you can see that we do have very vital FinnCERES company ecosystem comprising large enterprises and SMEs and startups. We have been able to generate spin-offs from flagship, and especially the collaboration with leading companies has been very successful, and also the new research program related to emission-free pulping has taken the first steps in the frame of FinnCERES as well.
Okay. And another thing that is very important is, of course, to educate the future leaders. So education and career building has also been a crucial part of the FinnCERES ecosystem. So we have over 70 doctoral and early career researchers have been supported. We have also supported their possibility to go abroad and broaden their expertise by using this Go Global program. And maybe the largest impact we had in this was that the Ministry of Culture and Education funded the Simanet Doctoral Education Network with 67 doctoral positions across 9 universities. And we also have been recognized as for our understanding of this field. So both Tekla and me, we are part of the Forest Bioeconomy Science Panel, where we are giving science-based science-based advice to politicians. We are commenting political decisions. We have also been collaborating with the Unite flagship and having some successful high-profile events in Finland and Brussels. And we have the international visibility through the Boreal Alliance Network, and our scientists have also been rewarded a lot for their scientific breakthroughs.
And as mentioned, we are coming to an end with this first period. I would like to see it as a first period of FinnCERES and first period of flagship program. And I would like to highlight here that we are already thinking of FinnCERES 2.0, rejuvenated flagship. And what is actually very crucial, what this slide, what we would like to share with you here is that these flagships are truly integral when we are thinking about the really strategically steered research, which is rooted in scientific excellence with industrial relevance. And I would say that having this type of entity, that's very unique in Finnish standards, also I would say the first one of its kind. And it is really allowing us to push forward our key research efforts towards the innovation path and towards the industrial implementation. And very shortly, just a few highlights what actually FinnCERES flagship has enabled to us and to Finnish and Finland's, I would say, research and also innovation ecosystem. And these numbers are kind of the KPIs, what we see, and when we compare the time before we have had this type of the larger entity, larger program pushing forward these fields, what we find important in Finnish economy, in society, and also as a research community. And with these words, I hope you enjoy these 2 days with us, with our program, and I will now give over back to Nina.
Thank you so much, Nina. I'm super excited to be here in Helsinki again in this beautiful building, Dippoli, where I spent very long times and hours. Actually, in the inception of FinnCERES, so I'm very proud that really bear fruits, and now we have a FinnCERES that is thriving, and for the future, I think offers great promises. So congratulations to the FinnCERES team. You are doing an amazing job. We're trying to do something similar in Canada, and I think together we can really work this out in a very synergistic way. I would like to talk a little bit about Beyond Wood. Wood is not my really area of specialization, but I think it's important for us to increase the awareness of the opportunity of this beautiful material. And first, I would like to acknowledge the researchers that are working with me in UBC, They are the ones that are doing the work, so really all the credit should go to our students. What we as professors do is to steer the energy and the emotion of the students that can apply their research and their creativity to create new materials, so all the credits go to them. I want to also maybe start my presentation by sharing a little more personal experience. That was a year and a half ago when I went to my home country in Venezuela. You know, Venezuela is really having a lot of trouble. It's a country that is in a difficult situation from the social, political, economic point of view. But there are great people still there doing very amazing things. And I met this toy maker in my hometown. It was a very short visit that I made after 15 years since my absence. And I like it very much because he was so passionate about the toys that he designs. And here he explained to me that the earliest toys were made from sticks, rocks, and stone. And we're talking, you know, quite a long time, 4,000 BC, years BC. And the toy evolution that he registered and he really shares with the visitors to his museum, that is one of the best for toys that I have ever seen, is, you know, the fact that toys started with wood, then moved to celluloids, then tin, then plastics, and now, surprisingly, back to wood. So this is really a very powerful message, because if you want to take one idea from this talk, is that wood is back. And that's why I want to maybe go deeper into this. Now, this is an old news, in fact. And maybe some of you know about this top story that I read about 2 years ago. The fact of the discovery of the oldest wooden structures in the border between Zambia and Tanzania. They dated the wood that was used apparently for some sort of construction, and it was 500,000 years old. So humankind has lived with wood, and wood has been essential in our lives. And always have been like this, but we have lost recognition to this fact. The same happens, by the way, to paper products, because we're gotten so used to tissue paper and the paper of every day that we forget to recognize the beauty of those materials that make our area very unique. I'm very proud to be a colloid scientist working at the interface in biomaterials, including wood and paper. In the bottom, you see a little bit, the little contribution from UBC to wood construction. But this expands also to the city of Vancouver, where a lot of wood buildings are being built. This one here is about 18 floors high, is all wood, and at the time was one of the tallest, or was the tallest building in 2017, not for a long time. Now there are many constructions also made of wood, and there are many architectural codes that encourage wood for construction. And that includes also not only North America, of course, Europe and South America, where there is plenty of wood. All to say that we are back to the future. And you know this very well because you have heard the news about invent wood, transparent wood, and many other discoveries that are not really as new. Wood, in the way of densified wood, has been around since a long time ago. The first time I heard about super dense wood, a journal contacted me to give my opinion, and then soon after, a fellow from Finland called me. We're doing densified wood since a long time ago to build bridges. So this has been really there already. What we're doing is pretty much reinventing and advancing, pushing this to the boundaries. So I here want to say that I admire wood, even though if it is a newcomer in my research. And one area that is very important that I see very strong in, of course, Aalto, but also in other jurisdictions like in Switzerland, where there is great research in the area, is the design of the smart wood buildings. This is very incredible. If you think about the different properties and functions that you can apply to the wood material that is used for living, for our livings. So this is really quite nice to see. It's very well advanced. And I love, as an example, the living lab that they have, where a great deal of their construction is wood-based, but also use advanced materials like cellulose aerogels for thermal regulation and other facts. So this area really, I think, can take a boost in the coming years if we start with wood. Think about nanocellulose. Nanocellulose is having a little bit of a delay coming, but I see great promise as far as wood. So I want to talk a little bit about some few properties of wood that can be endowed to the material by playing with very simple chemistries. The piece on the left is a tree in North Carolina that my son cut. The tree was dead. It's a cedar tree, and that really fascinates me, just to see the beautiful grains of that piece of wood. I mean, it's amazing material on its own, and the reason why it's built in such perfection to have given functions. But I want to introduce some new functions from the point of view of technology of wood. Circularity, strength and transparency, being soft and resilient, and also can be electroactive. And if I have time, also maybe add a little bit of functionalities. And this is work for the last pretty much 2 years in our team. I will skip the black wood that here Bruno leads with bean that has been amazing in Aalto, right? Black wood, super black material from wood. I will skip that because I think you all know about those developments that are really amazing, and I think Aalto should feel very proud. I use here one aspect or one illustration that can be quite useful to think about circularity. And I have presented this in several places, but anyway, I want to bring it back because it's so important that we think about circularity. If there is a topic that we need to really invest time and effort in circularity, and of course, using bio-based materials for the purpose of defossilization of society. So using recycling materials is becoming very important. The circle is a time span of 600 years or 500 years. And of course, if you think about wood for construction, you have already a couple of things that are important. The fact that we're capturing CO2, and then we're using the captured CO2 in long-lived materials that can last for not only 600 years, it can last thousands of years, if you think about constructions like pagodas in Asia. The problem is with the modern construction, for given reasons, we tend to go very fast and have, the need to rebuild cities. And that means that there is a lot of wood residues from demolition. And that's an important topic. And we have done a little bit, have looked into the data. And only, for instance, in the American municipal wood that is used, you can really appreciate by this plot on the left, the amount, the volume of wood that is used in construction and demolition, but it's just a waste. Only a very small amount is utilized again. And there is the statistics for one city of Vancouver, that is actually not too big of a city. Major issue. So since I talked about interfacial engineering, now we'll spice wood with interfacial approach to solving this problem. And this is already a publication that we have from a couple of years ago, but I want to bring it back again. And maybe I have presented this here in Aalto, but anyhow, I think it's important as a reminder. Essentially, what we found is that regardless what type of wood you have, that from waste wood or decayed wood or sawdust, if you take that material that is really deconstructed, broken down into pieces, by doing delignification, that by the way is a procedure that is also used currently for densified wood, then you can really start to drill in the properties of cellulose so that becomes the main actor. And for that, the concept here is very simple, and we have used this in many other applications. This is just the beginning, but currently we're doing many things with this idea of interfacial partial dissolution of cellulose. Essentially what we do is we take the delignified wood, we apply a solvent for cellulose. That solvent will trigger dissolution only at the interface because of the conditions that we use, and that dissolution, partial dissolution, will unravel the nanocellulose that exists already in the cell wall of the fibers. So here we're talking about nanocellulose, but it's a nanocellulose in different form. It's the in situ nanocellulose that we have that then we open up by dissolution and now regeneration. So the green colors that you see there in between is the nanocellulose that regenerate into cellulose, solidify, and then can heal the material together. So it's dissolution at the interface, nothing is removed, the yield is very high, 100%. We're not removing cellulose, we're just dissolving it and then regenerating it in situ. And that really produces this self-densification of wood. Very simple concept, but it's different. It's different than what has been used so far. And at the end, we got, very interesting results if you think about the mechanical properties of the wood material that is used. Now, bear in mind, doesn't contain lignin. That's a price that we need to pay. And I think there is a possibility to still keep lignin there. So very important, very simple, very fast. You got the idea. Now, what if wood is not only used for structural applications in the sense of the high mechanical strength that was recorded and you saw? It's already very high. But what if we make it also transparent? And what if we make it good thermal regulation material? That would be a next step that I would like to share with you using the same idea of interfacial phenomena, doing a little bit of magic of chemistry at the interfaces. The fact is that in our houses, we have a number of surfaces that are covered by glasses, like in windows, and this is where the energy, or great deal of the energy is lost. 60% of the energy can be lost due to poor thermal properties of the glass materials. And when it comes to transparency, also for windows, the fact that we have air-cell interfaces, the fact that we have air and solid interfaces that scatter a lot of light, together with lignin, we have an issue with transparency. It cannot achieve good transparency. So this is a problem in the case of the glasses where we lose most of the energy. So that brings the idea of transparent wood. Transparent wood has been around already, right? Quite a long time. Our colleagues in Sweden, in KTH, our colleagues in Maryland also have been working on this. But what I will present is a little different spin to that work inspired by them. So delignifying and infiltration is what has been done so far. What I offer here is a different approach, also very simple, and playing with well-established chemistries. And here the idea is just to oxidize cellulose. Again, we start with a partial delignification. We do oxidation with periodate, and that means that the cellulose chain will be converted in such a way that we will install aldehyde groups. And that conversion of the C2 and C3 groups, OH groups, into aldehydes can really trigger binding between the interfaces by just dehydration, by adding water, removing water, and then by pressing, then we can have this cross-linking that is very strong. And that will give us a piece of wood that has water resistance, is densified, as I will show, also has very interesting thermal properties. So that's what we do here, and I will go here very briefly about the evolution of the material. On the left, a piece of wood, in this case, it's low-density wood, cross-section, and then the plain view of the piece of wood, that would be the original wood. Delignification, then we gain, of course, in density, as you already saw. In the cross-section, the material will be densified quite a bit, and then you see the different changes that have happened. Light absorption will be reduced, and that's a gain. Now, we take that and oxidize these to aldehyde groups, as I indicated earlier, and then you see there the type of wood that becomes transparent and the increase in the density that is quite large. So that means that now we have a delignified and dialdehyde oxidized cellulose in the wood that makes a material that is strong, dense, and transparent. And if we create laminates based on these pieces of wood, then we can have a multi-layer structure, 2 or 3 layers, and those can be shown in the bottom. DOW means delignified, oxidized wood, 3 layers in a crisscross configuration. And what we notice there, as you can appreciate here, is that from the original wood to that one that we have at the end, we have a tremendous increase in the tensile strength. So again, that was expected, given what I explained earlier. The wear strength is also very high, as you can appreciate here, in the case of the wood, and the last piece of wood in the 3 layers that I show is quite good. And the resistance is there. So amazing material, very competitive by all means with many other types of materials. If you look at the bottom, sort of a low resistance of this piece of laminate. But the point here, of course, is that we also gain transparency. And the transparency, you can see, is going to increase as we go from the delignified, densified wood to the oxidized wood. Very interesting. As well as the haze. There is here quite a nice gain. But the most important part is that this sort of glassy wood has a very high effective thermal resistance, or measured by the thermal conductivity. You notice that compared to glass, there is a drastic reduction in the thermal conductivity of these pieces of wood. That's shown in the experiments above, just to measure the temperature inside and outside a material that is built with glass and also with this type of wood, and the performance is remarkable. So these are little examples of things that you can do if you play with interfacial chemistry, with colloidal science, to make a piece of wood quite functional, and goes beyond the concepts of transparent wood that requires infusion of an index match polymer. We didn't do that. And also you gain in thermal properties, right? So no infusion of polymer. That's important to highlight. Anyway, but the beauty is that now we also show that wood can be not only strong, but can be quite compressible. And we go now the other way around. And I only show 2 slides to illustrate my point. Very simple as well. Soft and resilient. And what that means is that we do exactly the same that I showed earlier. We take wood, selective remove lignin while maintaining cellulose and hemicelluloses. This is possible. So it's a hollow wood. Hollow in the same sense that we use in paper making. Remove lignin, but we kept hemicellulose and cellulose. And then we do the oxidation, as I have explained already, to aldehyde forms. But then we follow it with reduction, with borohydrate. And that means that the aldehyde groups now are converted to alcohol groups, dialcohol groups, and that brings a material that is based on cellulose, but the chains are disrupted, and that means that now it's compressible. And as a matter of fact, after this process that we call amorphization, because you are reducing the crystallinity of the material, you get a foam. So we're going all the way around. We know about foam forming, we know about making foams in different ways, but this is really a very simple way that directly from wood we can get a material that is compressible in one direction. It's compressible in an anisotropic manner. So it's very compressible in that direction, but in the opposite direction it's not going to be. And of course, you can then play to make it fully hydrophobic, and that will be the block on the right. That attracting a lot of attention of large companies in the area of electronics, because it can be used as a packaging material. You can make the shape that you want to store and transport electronic materials, and it's just based on wood, where you don't need to do anything, but just to do the chemistry and mold it in such a way that you get the material with the shape that you want. Now, again, all of this about wood has been known since ages. And if you go to the Museum of Anthropology in Vancouver, where Monika and Tekla came not too long ago in one of our activities, you really realize the beauty of indigenous communities that in British Columbia were working with wood to make amazing materials that didn't require any stitching, any gluing. Very important in a different context, as I show here. Finally, electroactive materials. I know some of the best wood science in the old times have come from countries like Hungary, where there were really great developers in the area. And some of the first reports about the piezoelectric properties of wood were reported by scientists from all these areas, right? We know wood is a piezoelectric material. If you deform, you can produce a current. Very little, but nevertheless, it's there. So it's an electroactive material. And we have shown this in the case of nanocellulose, amazing piezoelectric materials. Again, piezoelectric, to remind you, is a material where you can deflect and produce a current, or you apply a current and produce a deformation, right? So that is well reported. But what is maybe less reported is the use of wood in tribo generation. And tribo generation has been around for quite a long time with the work in Georgia Tech. Tribo generation means, as you know well, if you have two surfaces in contact, you can produce electricity. You can produce a current, right? And that's solid-to-solid contact. But we wanted to go here a little bit further to make solid-liquid tribo generation. So this is what we did in this journey, very, very recent. We took wood. This is a cross-section of the cell wall of a piece of wood. And then we dissolve lignin. But rather than extracting lignin, we kept the lignin, and what we found is that it clustered and formed particles in situ. So we don't need to dissolve lignin. And this is also some work that Bruno, Bean have also shown in a different context, adding particles to wood. But here is the idea to dissolve the lignin in situ and then cluster it into particles in situ. We're not adding lignin, it's just the native lignin. And that's what you saw here in the bottom, with that lignin that is coming out and is going to go to the surface. So again, here we're looking into interfaces. And that type of the lignin that is produced essentially from this process makes the wood hydrophobic. And what we found is that by that simple process of delignification and lignin clustering at the interface in situ, the lignin will go to the surfaces, and that includes the external surface, and now we have a self-hydrophobization. That's what you see in the bottom. And that triggered the idea, if we have this, what if we drop water on that piece of wood? And then this is the example on the right. So it's the idea of contact electrification, solid liquid type tribo generation. Essentially dropping a droplet of water. The droplet of water hits the surface, slides, and then will be a tribo charge that is going to generate. I won't explain the details because of time, but it works. That's the point here. So this is charge exchange with water, mimicking the rain. So it's a rain-driven electrification of wood. And then we tested that, and it's possible, it works. The energy is very small, so don't think about this as a way to, to illuminate a city, but to be locally used for the needs in a wood for construction. So here we have the summary of the results. First, the self-hydrophobized wood, very strong as far as water resistance. And then by playing with this sort of setup, some pieces of wood, not as large surface areas that we need a bigger, system. Nevertheless, we play here with a rainfall, simulated rainfall. Probably can be better, especially in the city of Vancouver where we have a lot of rain. But you see the point. That rain impacting the pieces of wood is able to generate enough current to light up the given LEDs that you see in the bottom. So wood for electrification. Very nice if you think about this idea for possible deployments. Anyway, I will end up in the last 4 minutes that I have to talk about what to do with the lignin that was extracted in the 3 first examples. With the lignified wood, except for the last example, what to do. And here I have 2 cases, lignins and tannins. And I don't have time to go to tannins, but I want to show only 1 case for lignin, because it's important, because I want to drill in our minds the idea of the standardization of lignin utilization. So what to do with the lignin that we remove from wood. And you already know that lignin for carbon material is a very hot topic. Here in Finland, we have some spin-off that are looking into hard carbons from lignin. Here in Aalto, you are doing also carbon filaments based on different wood components. And here what we wanted to do is direct lignin to supercapacitors, right? And the concept is very simple. It's just to use lignin as lignin-based electrodes, covering a liquid electrode and a separator so that we can have coin cells types of supercapacitors. So these are the sort of the sprinters in energy. We're not talking about batteries, but supercapacitors. Low energy, but fast charge and discharge, as opposed to batteries that are the marathon runners. But the one thing that I want to say, lignin is amazing for this option. Lignin is an amazing possibility. But what is the challenge? We are so confused about what lignin to use for those and many other purposes. And this is something that I started to do here, actually, with Patrick James, Misha Balakshin. We started to look into artificial intelligence to understand how to use the power of AI to come up with the optimum lignin type. And the problem is that we have different plant feedstocks, different origins for lignin, different processes via the pulping process. So we have a confusion with the lignin types that is accessible to us. And what I ask a couple of students in the group is to collect lignins from around the world, technical lignins, craft, lignosulfonates, soda lignins, enzymatic hydrolysis, and organosul, to see if we can profile those lignins, generate data, and using machine learning to really drive discovery of lignin utilization and really select the best option for lignin. I have no time to go into those details, but this is work in progress. But the idea here is to look at the lignin source, unveil, study the structure, look at the macromolecular properties, the material performance, and then see how they can be used, either for carbon fibers or, in this case, for energy materials, right? And the design that we came up with is this one, very simple, very short. It's just the design of a supercapacitor in a coin type of battery, or supercapacitor rather. In this case, we selected to use lignin particles. It's much better for us to understand lignin if we put them in the form of particles. And that's what we tested here. On the left, some metrics about the energy and the power density, more or less about the speed at which the energy can be used. And then, of course, we found that that works quite well. This is unoptimized. There is much more to do here in Finland and many other jurisdictions. There is a lot going in this area, and it's very important that we think about it. Because in this case, what we found is that the performance of this lignin carbon outperform that of the typical carbons that are produced from, biocarbon from coconut shells, right? These are the benchmark, in many cases, the use of coir fibers. So this is pretty much what I wanted to say. I have something about tannins, but I think the time is up. It's only 1 minute left. And I wanted to close here with this idea that I tried to push in Vancouver and actually across Canada, trying to create a FinnCERES type that was led with us. And that was the conception that we came up with discussions with industry and the many faculty that are in University of British Columbia. And I want to bring that as a bigger picture, perhaps, for FinnCERES in the future, where we need to consider the different stakeholders, especially community. The social sphere of our work needs to be connected with the communities. And then, of course, access to the fibers that should go beyond the forest, but also very important, we need to emphasize the use of residues, transforms and translate to make a difference in the future sustainable economies. That's all I wanted to say. It was only 30 minutes, and I think we have now 4 or so minutes for questions.
So thank you for the invitation. It's really a pleasure to be here in front of you. I've never been in this hall before, so I haven't graduated from this university. My background, as already told, is totally different from yours. And if you guess who is learning most today, it will be me, because everything what you tell to me is new for me. I have been discussing with Tekla and Monika a bit, so I know some basics, but my capacity to adopt your knowledge is hopefully good today. So anyhow, I will walk to the forest and to peatlands with you. This is not recreation activity at all. There is lots of challenges in forests and peatlands, but there are also possibility for solutions, and I wish that we find them in collaboration with you. So this is my title today. They are already in the program, but I will start with the global challenge. And global challenges are there, and some solutions are hiding there in the forest and peatlands. Global challenges, there are a few of those, but the climate change and loss of biodiversity is one of the big ones. And we know that greenhouse gas emissions, they have increased more than 50% since 1990. And 1990 was the year when United Nations framework for climate change was established. So the process haven't been very successful in reducing emissions. Maybe some we can assume that they would have accelerated even more without any actions, but the actions what we have taken, they are not enough. We do have climate targets. We are aiming to limit the climate warming to 1.5 degrees Celsius. And in this, in previous slide, you see the total emissions at the moment. They are 57 gigatons of CO2 equivalent. And here on the figure on left hand, we draw the line what should happen to reach this 1.5 or 2 degrees Celsius target. And we need lots of mitigation actions in all sectors. And this figure on right-hand side illustrates what opportunities we have in different sectors with the prices less than $200 per CO2 ton. And today I will focus more on this green part, which is forestry and agriculture, and under the forest there is also activities which deal with peatlands. So I'm digging on that, but remember that there is lots of opportunities to mitigate climate change also in the other sectors, and all the sectors have to do something. I dig a bit deeper to forest-based climate change mitigation potential and Europe. This is one of the review articles where I was part of, and we analyzed what is the mitigation potential in Europe based on review, based on existing literature. And I want to emphasize the bars which are there in the middle. There is forest management activities which play a role, and decreasing harvest play a role. So they by transition to more sustainable forest management practices, we can increase forest carbon sinks and mitigate climate change. And by reducing harvest, we can do the same. If we increase the harvest, we lose the carbon sink. And I think that discussion here is just there in the topic that we have to make higher value with less biomass, and we have to use alternative biomass sources. We cannot kind of increase all the harvest all the time to serve society. We have to find better solutions. And then the highest bar, actually, there is a forest restoration, which means peatlands restoration. And this indicates that there is lots of opportunities in land use sector to reduce emissions by climate-wise management of peatlands. This illustrates the area of peatlands in Europe and how peatlands are used in Europe and what are the emissions at the moment. And from the figure on the left-hand side, you see that the size of the symbol illustrates the area of the peatland, and the colors indicate how the peatland is used. And in Finland we have a green and grey, unless this orange color. Grey means that it's natural peatlands, and green means that it's converted to productive forest by drainage. So they are heavily managed, they are drained, they are drying, the peat is decomposed. And that activity is kind of dominating in Finland, not that much in Sweden. In Sweden, they have more untrained natural peatlands. And how the peatlands are used in Central Europe, they are used mostly for agriculture. And we know that emissions from agricultural fields, they are higher than from the forest, but both of them are emission sources. And on the right hand, you see the figure. Note that there is logarithmic scale, but the highest emissions from organic soil, so the soils of peatlands, are from Germany and Finland, Ireland, UK, and even Netherlands. And in Finland, they come mostly from the forest, and from Germany, they come mostly from agricultural soils. So now, at European scale, we say that we have to find climate-smart, climate-wise management practices for agricultural fields on peat soil, because they are high emissions in Central Europe and also to some extent here. And then we have to find climate-wise solutions for management of peatlands, forested peatlands, which is a big issue in Finland and Baltic, where we have high emissions from there. So what are the drivers of the peatland management? Land use, first land use. This is a pretty typical map, part of the map from Finland. Untypical is that there is some untrained peatlands, which is nature conservation area. There is a nature park, Kansallispuisto there. But if you have a managed landscape, there is the ditches. All these blue lines are ditches. They have reduced the water table to 1 meter or somewhere pretty deep, and all this aerobic peat layer is decomposing, and the speed of decomposition depends on water table, how deep is it, and how fertile the soil is. More fertile, quicker the decomposition is, and the lower the water table, higher the emissions. So land use, we have this drainage is kind of dominating our peatland landscape. And then management, we can do management in different ways. And in case of forest, unfortunately, the main management practice is to do the clear felling, as you see, relatively large one in here. And the ditch is this happy one. This is the old ditch covered by sphagnum mosses. But if it's open, it's the source of methane. In this phase, it's not. But anyhow, it's land use and management practices who drive this process. And this is the global meta-analysis where they kind of show that in peatlands, the water level affects soil greenhouse gas emissions. And the deeper the water, the higher the emissions. And there are different emissions. There are CO2, there is methane, and there is N2O. And while this drainage increase CO2 emissions, it might slightly reduce methane emissions. But the driver here is the CO2, and also methane emissions are there from the ditches. But anyhow, the rule that lower the water table, higher the emission, it's confirmed at global scale, and it's evident in Finland, and we have lots of measurements of that. And it's also visible. This is this figure here, photo here. It's from Finland, and in our case, trees do not have this stump and root system that there is hollows in there. This is created by decomposition of the peat. There is kind of a 20 to 40 centimeters peat lost during the growth of these alder trees. This is Alnus glutinosa forest, but there is kind of you visually you can see that the peat is decomposed and a lot of carbon is lost during the course of the 40-50 years. There is already policy targets here set to to land use sectors at EU. There is LULUCF regulation. LULUCF comes from land use chains and forestry. And according to that regulation, which is agreed at EU, in Finland, LULU sector should be carbon sink of about 4 million tons of CO2 equivalent by 2030. In addition, we have national targets. We have a carbon neutrality target by 2035. And Finnish climate panel, where I'm part, we calculated that to reach that target and after estimating what other sectors, all the sectors could do, according to our estimate towards carbon neutrality pathway, Finland should have a carbon sink of 50 million tons of CO2 equivalent by 2035. Sorry, there is a typing error. The year should be 2035, which is our climate neutrality target. In addition to that, there is also other regulation at EU level, and most important is the nature restoration law. There is where we have requirement to revet peatland fields, agricultural fields on peat soil. And there are targets for 2030, 2040 and 2050. And by 2050 we should restore 50% of our agricultural land on peat soil, which means that we should restore kind of 135,000 hectares. And we should revet almost 50,000 hectares. So this will be a big issue in Finland, where we have lots of peatlands, peatland fields. So what we could do, some solutions from forest and then from agricultural fields. This I can skip because I already told that we tend to have increasing emissions from peatlands forests. But the possibilities how we could manage them. Upper line illustrate the case when, after having a mature stand, spruce-dominated stand, normal conventional practice is to do clear cutting, and then we have high emissions, and it takes long before we have a biomass carbon sink. Alternative is to continue with the thinnings. We do selection harvesting and keep trees there. And by doing that, we don't have to manage ditches. So ditches are there. They are filled by mosses, and so slowly we get rid of these ditches without huge effort to do anything special. That's what we what we are testing at the moment. And this is just to illustrate that we have measured the emissions from both clear cuts and after selection thinnings, and I don't go into these details, but overall calculations show that if we switch from clear cutting and this rotation-based forestry to continuous cover forestry on these peatland forests where we have high fertility and drainage at the moment, we could increase forest carbon sink by 1 million ton CO2 equivalent by 2030. So this is the outcome. It's not huge, but it's improvement if we do that. And then what we could do on on agricultural peat soils, revetting for paludiculture or revetting for sphagnum or restoration for original forested peatlands, we have an emission reduction. If we have a cropland on peat soil, emissions are approximately 30 tons of CO2 equivalent per year. And if we do some revetting or paludiculture, it's decreased. And we do have a lot of these peatlands which are kind of potential. We have evaluated where they are and how much they are. We came up with the estimate that about half of the peatlands could be revetted according to topography and the wetness indices. And this is very theoretical calculation because this won't be realized. But if all this would be revetted, we would reduce emissions by 4.5 million tons of CO2 equivalent. And what to do with these revetted peat soils? They can be revetted to forests, birch or alder. They can be revetted for crop production, and one of the potential crop species is cattail, Tupha latifolia. It grows on forest, and it's well known. There is a well-known use for many parts of the plant. Actually, all parts can be used for something according to traditional knowledge. But then we can also test what is the potential for new high-value nanomaterials, for instance, and that's what we have done together with FinnCERES, or actually FinnCERES had done the work. And we have shown that cattail might be an alternative source of lignocellulosic biomass, and it provides high-value nanomaterials like lignin nanoparticles and cellulose nanofibrils. And I don't have to say more about that because there is a poster by Ikävalko and others to show more about this work, what we have tested. And then summary of my presentation, I have a couple of points. I want to emphasize that mitigation of climate change requires further emission reductions from all sectors. It's not only what I talk, it's all sectors. Otherwise, we don't really stop the climate change. And land use sectors, in land use sector, peatland management has a high potential to provide a solution, and we have to really change the policies and practices there. In peatland terrain for forestry, greenhouse gas emissions can be avoided by avoiding clear cuttings and ditching. So if we stop that and find an alternative way to produce biomass on peatlands, that would be part of the solutions. And then high greenhouse gas emissions of agricultural land on peat soil can be reduced by revetting and paluriculture. And one of the species is cattail, and it has a high potential, and we certainly need further studies how that could be utilized as a source of biomass. So thank you.
Thank you. Okay, thank you. So, I'm here to talk about carbon. Carbon is one of the fundamental building blocks of chemistry and life. And we all know lots of things that are made of carbon. And this talk continues the excellent talk Raisa Mäipää had before coffee. We know what we need to do science-based, but in the political landscape it is not always so easy because there are winners and losers, and politicians always want to take a stand and promote something which is not always what we want. Okay, so I represent LUT University that does stuff with the energy transition, which is an ongoing process, and you all here are part of the energy transition making things happen. So I discuss first why we need bioenergy, I talk about how to be carbon neutral and what this means with the carbon dioxide, my topic, and also in what it means in Finland. There is a lot of discussion that has been going on whether we can get all our energy from solar and wind. Right now it seems, based on LUT modeling, that this is not practical, economically practical. Everything can be done if we have infinite resources and infinite money, but for society it seems that we need something during the times that we have Dunkelflaute, meaning that there is no wind, no sun, and this can be for weeks in the fall time in Germany. Okay. And now let's talk about science. And here we have International Energy International Energy Agency's net zero emissions scenario, and we can see that yes, there's lots of biofuel production and there's lots of carbon capture and storage, but this is something that we shouldn't talk about because politically this makes problematic things. We discussed, okay, whether should we use land for agriculture or to produce biofuels, whether we should promote CO2 or not, and these are things that we haven't politically yet solved, even in Finland. Let's talk about fossil-free steel. So this is a hybrid project slide, which is a big Swedish initiative where we would decarbonize steel making by using hydrogen. Something is missing, which we see here, in this slide, down here. There it says bio. Also there is some coal. Why? Because we can't make steel without having some carbon. If we make steel without carbon, it's fragile, there is very little strength, we can't make tools, we can't make cars, it's unusable. So we need some carbon, okay? We need to put some biomethane, some biocarbon, stuff like that to make this happen. But again, in this environment, guys who are promoting fossil-free steel, they are promoting hydrogen, they tote hydrogen, and they never mention biogenic carbon. Then we have European Union. Here is the official European Union slide where we notice that there is greenhouse gases going down and we have net removals. Part of it is natural processes, but part of it is new human-made sinks, for example, capturing CO2 and putting that, for example, in the underneath North Sea bed. But do politicians talk about how this is achieved? No. Again, this is something that one shouldn't talk. I was in first carbon capture negative CO2 emissions conference in Sweden, in Gothenburg, and we were welcomed by a speech that, are you going to ruin the whole fight against climate change? If there is carbon capture, then all the coal boilers in Germany are going to continue operating, and then this is your fault. Yes, this is. So this is something that is problematic to me, that you kind of say that only some solution is available and some other solutions can't be used. And the NGOs there present said that as long as there is coal firing going on in Germany, you can't talk about that. But bridges are breaking. Why do I say that? Now, in German environmental ministry's web pages, there is a mention of CCS, one single mention. But until now, it is half a year ago, there wasn't a mention of CCS. So, environmental ministry was totally silent about possibility of carbon capture, even though European Union says that this is what we need to do. Science says this is what we need to do, but we can't do because of stuff. This is my own graph. And you notice that Raisa was talking about carbon neutrality in 2035. I'm talking about carbon neutrality 2045. I extrapolate with the blue slide how the Finnish fossil emissions are going down, and I have put down my own opinion of what is going to be the LULUCF, so natural stuff there. Now we are, unfortunately, we have gone from highly negative to positive because of increased temperatures, for example, one thing. And this is a big problem. The same problem occurs in Germany, in Norway, in Sweden. So this is not a Finnish problem, this is a European problem. Then just extract from LUT work. This is done for the Greens of European Parliament. So it is published by the Greens of the European Parliament. This is Europe without nuclear, but we notice that this is not Europe without bio-based stuff, and this is not Europe without carbon capture and carbon capture from biogenic sources. So basically we have also an estimate made by the European Union Joint Research Council of how much carbon capture we need to get. Based on them, most of the carbon capture is going to be put underground, so we make negative emissions. Why do we have to make negative emissions? Because Europeans have been putting out carbon long time, so we want to kind of make good on our previous sins. But a large portion goes to synthetic fuels and a large portion goes to materials production. This is another thing that we should talk about. Where do we get carbon? If we are, European Union is fossil free in 2050, so we are not using oil, we are not using natural gas, so how are we going to make plastics? How is our clothes, textiles going to be doing? Where do we make airplanes run? How do we make a marine operate? We need some carbon source, and this is something we should already start promoting. So it is either bio-based or recycled, and when I say recycled, then recycling atmospheric carbon by carbon capture is one of the best ways of doing recycling. This is Finnish chemical industry's future outlook. So they are now using 22 million tons or doing stuff. And they think that in the future, okay, they still have some fossil-based stuff in 2045. Biogenic part is very large. How? You guys are there to discuss, to formulate that, but also there is some material, some amount that is coming from carbon capture and storage through e-materials and e-production. Europe has big CO2 potential, but it is going to be a tight fit, so we need carbon recycling, so we need waste recycling to be helping us. Finland has a very big economic possibility. We have possibility of 20 million tons of biogenic capture, and if we make half of that to biomethanol, then it's about 8 billion euros. And if same would be made to hydrogen, it is only 3 billion. So the more we manufacture, the more we do, the better we are going to be doing. And yes, Finland has one of the lowest electricity prices in Europe. We have been able to keep the low price, and it hasn't increased like some of the Central European countries. Now I'm in the conclusions. So bioenergy, bioproducts are still needed in 2050, and in my opinion, the level of biomass usage in total in Europe is going to be about the same. We are not going to be able to increase bio-based utilization. And my idea is that instead of wasting money and putting stuff underground, we should be making more carbon-based e-materials for the European markets, especially because chemical industry everywhere around the globe needs materials. And aviation and marine, they need e-chemicals for fuels. Thank you.
Thank you so much, Esa, for
Hi, my name is Petri Laakso. I'm the CEO at Soletair Power. I've been with the company 6 years. I think Esa had a very valid points in his presentation, and I hope that I can take you even further in carbon capture and utilization. We do direct air carbon capture, so bear with me for a while. The company was founded in 2016 because the researchers at LUT and VTT wanted to have a device that could capture CO2 from air. Our founders saw on the newspaper that the researchers want to capture the CO2 from a point source. And he was just thinking that why don't they take it from the air, because that's why we have the climate change happening, too much CO2 in the air, and there's technology to do that kind of things. And the first pilot was ready 2017, but we noticed the problem, what Esa was saying, actually the factor was like tens of times more expensive than point source capture. And then we did the pivot that hey, what if we would use the world's biggest infrastructure that pumps air 24/7, 365, so the ventilation in buildings, and utilize that airflow. And what if we could save energy while doing that, and this way this could be profitable and we could make nice things with it. So that's why we pivoted back in 2017. And nowadays what we say is that we want to convert buildings into CO2 capturing machines, because basically in buildings the air temperature is the same, whether it's Finland here in the winter, Dubai in the summer, it's always plus 20, air is clean and super high stability. And buildings ventilate so much air on a yearly level that you can capture gigatons of CO2 from the ventilation. So the air is already moving. There are many other direct air capture companies that want to build another infrastructure to move that same amount of air. And to give you some numbers, you need to have 1.7 million cubic meters of air moved, and then you can capture 1 ton of CO2. So if we speak about capturing gigatons with direct air capture, we start to change the weather. That's the amount of air that you need to move. And why do we then focus in buildings? If you go and look the International Energy Agency's website, 38% of energy-related CO2 emissions are because of the buildings. 38%. That's a big task to solve. And 8 is the construction and embodied carbon in buildings, and 30 is the operational emissions. And out of those operational emissions, ventilation is 40% on a global average. But if you go to Dubai, Singapore, Hong Kong, that's 80%. So if you could do something with that, you could reduce the energy consumption, and if you would use direct air capture, you could capture a lot of CO2, whether you could bury it permanently through mineralization, or you could utilize it in applications. I will show you what we've done over the years, quite nice things. And as you can see, the Antonio Guterres, UN Secretary General, has said that cities are the place where we will lose or win the climate battle, because most of the energy is being used there. And so what we want to do is that we want to revolutionize the building ventilation business, because there's a lot of inefficiencies. We are ventilating too much. We have a room here full of people. You probably can hear the ventilation running. It's drawing from outdoors. Let's say here in Finland it's not not that cold at the moment, not that hot. So you don't need to spend so much energy on cooling or heating it. And you don't push that much of a cooled air out to hot temperatures. But if you do this in Singapore, this kind of auditorium, you need a couple of 100 kilowatts of power to cool down the air and condensate the moisture away. And if you can take half of that away, you will start saving a lot of energy. And then if you imagine the whole city doing the same thing, that's a big difference. From a single office, you can capture like hundreds of tons to thousands of tons of CO2, office building, in a year. And it doesn't sound that much, but then if you think about that, you would have a city full of these kind of buildings, it starts to add up. And like I said, if you would do a global deployment, it could be gigatons. So what we do is that when in buildings you push in air, we can capture CO2 away, and that lowers the demand for fresh air. There's basically CO2, what we exhale here, needs to be diluted and taken out. So if we can push in 0 ppm air into the building, you don't need to ventilate so much. Well, then there are VOCs and such that you need to still have some sort of a fresh air ventilation. We can also take more than the atmospheric CO2 if you take the CO2 from the air going out, but then we cannot make any energy benefits within the building. If there's a recirculation, like in the hotter countries, then you can combine both, maximum CO2 capture plus the energy savings. We think that the mineralization, for example, in the concrete industry, would be a good utilization case, because then they can substitute part of the cement and make even net zero concrete products, what we've done together with a VTT spin-off called Carbonate. What we claim is that we can save at least 50% energy in the building ventilation. And that's the biggest consumption of energy in buildings in the world. I think Esa was mentioning about net zero. We want to take it to the net negative side, start speaking about regenerative buildings. Buildings that start to regenerate the nature instead of burdening it. So that even though you use energy and you have embodied carbon in the building, over the course of the lifetime of the building, it captures more, and so the balance would be negative. That's something. In Denmark, here in the upper right corner, you can see how the, oh, well, you cannot probably see, but there the blue circles are the legislation in Denmark that you need to lower down the emission class of a building to get a building permit. And with our technology, through negative emissions, that's much cheaper than using novel materials at the moment. So that is what we are doing in Denmark at the moment. We are building a office building, and we are making negative emissions. That building is 12 kilos per square meter per year emission class, and with our technology, it's 6. So, and if we would install the unit on the inlet side of ventilation, it would be close to 0 when we utilize the negative emissions. Well, what about the economics? If you have a 2,000 square meter office space in Singapore, you need to ventilate like 3 cubic meters of air per second. You need like 250 kilowatts of power to cool down the air, typically all year round. And that means that if you can save a lot of energy, like what we say 50% at least, you save tens of thousands of dollars a year. That pays for the DAC, and then it ends up that actually you start saving money instead of spending money, even though we also use a little bit of energy, but the savings is much more bigger. So then we can even pay back the capex much faster. Payback can be even below 1 year. On top of that, when the building saves energy, you also avoid CO2 emissions, which we don't typically kind of calculate in, but it's benefit for the customer, and making negative emissions. And here on right, you can see the big drop that if you start from, let's say, 32, 33 degrees Celsius, full humidity, you need to cool it down to 8, 9 degrees Celsius to condensate the humidity away. And that step takes a lot of energy. And when the climate is getting hotter and hotter, more we need to cool in the future. Well, any one of us, if they've been in a meeting room full of people, have felt that I get tired quite soon, or you cannot really concentrate. That's at least according to several scientific papers because of the CO2 in the air. So if atmospheric CO2 doubles inside, you will lose like 20% of our cognitive function. So we can also keep that at very low levels if needed. And I will jump one slide, I will come back to the previous one soon. With Wärtsilä in Vaasa on their Sustainable Technology Hub, we have a system that captures the CO2, and we can keep super low CO2 levels within the meeting rooms there. And here we have a picture of meeting room having 160 ppm. Outdoors it's 420 or higher. And typically in offices it's like 600 to 800 and so on. That building is built 2022. And it has an on-demand ventilation. So CO2 level is controlling the ventilation speed. So there we can see the demand drop in the energy of a building ventilation. How much time do I have? Oh, okay. What does it look like then in a ventilation room? So here on left, you can see the ventilation unit, fresh air coming in from the lower left corner, going through the ventilation unit, heated, cooled, filtered. Then we capture the CO2 away, and then you push the air into the building to reach low CO2 levels. You can also capture it from the duct on top, which is the outlet of the, let's say, dirty air from the office. Some cases that we've done over the years. The pilot was back in 2017, but then for the Dubai World Expo, we delivered a unit 2021 that captured CO2 and water from the air in Dubai. From water we made hydrogen, and then we synthesized with CO2 the hydrogen to be synthetic natural gas. And there was a coffee machine that kind of burned the gas to heat up the water. So probably the world's most expensive coffee maker ever. But Power-to-X made actually 2020 already. Many people speak about it, but quite a few have actually done that. Then 22, we delivered just outdoor CO2 capture device to Germany. They make power to methane. There also, this was the Wärtsilä building. Next building, what we are now building, is the Danica pension, should be ready this year. They will use it for concrete. Solar Foods, startup from VTT, basically, they use our technology, that out-of-air part, CO2, coming out of air. Hopefully, the next case that we are gonna sell is gonna be the Hong Kong University of Science and Technology. They wanna use it for algae growth. Well, paying customers always right. I don't myself believe in those, but of course, it could be a good one. And how does this then work? So in a building, you capture the CO2, you have a tank next to the building, you use a tanker truck, take it to, let's say, concrete manufacturing facility, and then you can utilize the CO2. Or you can make fuel, many different applications, but humankind will build another set of buildings by 2050, so there's plenty of storage available and less cement utilization. And last slide, almost out of time. So there's many different applications for carbon capture and utilization, also for direct air carbon capture. So even fizzy drinks that we drink need CO2, goes back into the atmosphere, taken down again and reutilized. But we think that the building materials would be the best solution, but many utilization cases are possible, and of course fuels also. Thank you.
So nice to be here, and I was really amazed of the audience. You are so international today. And then talking after these excellent talks before, it may be that I'm repeating some what they said. But it is an industry view, but I would say probably that it's energy-intensive industry view. When we talk about hydrogen economy, we talk a lot about energy, and that's partly why I'm talking here. Metsä Group is most likely familiar to many of you, but we are one of the big pulp and paper companies. We have 9,600 people working with us. Pub quiz knowledge is that we are owned by, we are co-op, so we are owned by forest owners, very Nordic-based from that point of view. And this, I always have to say that this is the best way of capturing CO2 is to keep your forests in very good condition. There is the most of the value chain of our industry presented within the company. And then we have the innovation company that are most likely you also know, Metsä Spring, and there are people from our business areas and from Spring present here today. And then what I'm presenting is this renewable energy part. So last year we produced a bit more than 26 terawatt hours of energy in different forms. Oh, I'll skip that one. So But we've been investing quite a lot, over 6 billion euros before to date since 2015. There is a lot of different type of mills we've been investing in. So starting from the very left, there are the engineered products, kind of carbon sink type of products, going to different type of, for example, for buildings. And then, of course, we have the bioproduct mill in Äänekoski, which is, by the way, it is the largest single act in our energy efficiency scheme in Finland. Then we have the demo plant for Kuura textile fibers in Äänekoski. Muoto is also very brand new work we'll be working with. There is, for example, the new sawmill in Rauma is very efficient, very digitalized unit, probably the best in the world currently. And then recovery boiler in Husum, which was replacing a couple of old ones and really improved the efficiency. So we were working a lot with different type of investments and very new type of products. And then there is also different types of plant investments. And what I want to say with this one is also that we are investing, we are not kind of closing things down, even though currently our industry or the market is not at the best what it has been. It will be again, but this currently we are struggling a bit, this industry. And then Metsä Group energy numbers, as you can see, we are significant producer of electricity, steam, of course. Both of these are mainly consumed at our mills. And then we also have some sales. We purchase energy mainly of course, in Central Europe, where we don't have that much production of energy. And then also we are part of the emission trading system, and we do produce a lot of bioelectricity, about 15% in Finland. About 15% of bioenergy in Finland is produced by Metsä, and about a fifth of the bioelectricity in Finland is produced by Metsä. So we are a significant actor in the energy market in Finland. But then at the same time, coming from the energy side of this industry, it is really good that there is this crowd and you are developing new products so that the wood can be utilized and not used for energy production. But from the energy point of view, every time you do it, we need to find out new ways to keep our industry running, because we will be using that and needing energy in the future as well. So, this is then the bioproduct mill concept, and there are traditional products, there are new bioproducts, and then there are something that is under development. But the point here is to utilize every biocarbon molecule, everything that there is in the use, in the best possible way. Some of it is way in the future, tens of years from now, but then some of them are already reality. And the capturing of the biogenic CO2 is one of the ones that we think that there will be potential for chemical industry in Finland. And Esa showed earlier the bubbles in the Nordics. I'm showing only the Metsä mills. All these are now recovery boilers. We have other sources for bio-CO2 as well. But the thing with recovery boilers is that within a couple of decades, there will be the usage of the chemicals in pulping process, and we would need the recovery boilers for recovering the chemicals. And while we do it, we need heat, so we will be burning some part of the residues of the wood. and currently these are the numbers that we have as bio-CO2 emissions from the recovery boilers. There are other type of sources of bio-CO2. Some of them are used only for wintertime. Some of them are used for electricity production with the CHPs or so forth. But these are all, we consider the recovery boilers the most probable sources for bio-CO2 for the industry. All in all, when you look at the industrial bio-CO2 emissions in Europe, and the main sources of it are Finland and Sweden, and Metsä Group, the amount is about 6% of the whole Europe's bio-CO2. So there is a great potential for us. So how can we utilize the bio-CO2 and what is the value chain? So currently when I'm looking at this, there is a lot to develop. There are, like we have the renewable energy, we do have the electrolysis, we can capture the CO2, but there is lots to be done in order to make this feasible industry. Well, the top part there is the direct utilization, and currently there is already quite a lot of bio-CO2 capture, but it's not from flue gases. It's usually from sources where the bio-CO2 percentages is close to 95 or above. So it's completely different technology to capture that. But when we are talking about flue gases, the most used one is the AMI system, and there is about 50 plus utilities already doing this. Most of it is used for enhanced oil recovery, which is not, which one I'm not talking about that now, but then when you have that in large scale, you already have the pipelines for CO2, so you can directly push it back to the wells and then have more fossil carbon molecules coming up from the ground. But when we're talking about then utilizing it, so we will be producing something, there was in previous talk, there was already all kinds of these utilizations, what you can make with it. And there is a lot to be done. There is a lot of potential because there's some molecules, there are building blocks of different kind of chemicals. So that would be the new, and there would be a lot to do, lots to be done for the future industry and to make this feasible. Then, of course, there is the storage route that I'm not going to be talking about that much. But when you talk about the storage, there is the logistics and the transportation is one very large part. But then it is also for, of course, the other type of utilization. Well, the original picture that I took some lines out of it, but didn't change the timescales. That's from 2020, and this is the basis for a lot of EU talks on when the hydrogen economy is going to happen. Then this line was 25, 30, 35, so forth. But today we are almost in the same situation as in 2020 when this was made. So the kind of the hydrogen economy is going further. There are reasons. I know that there's been crisis, energy crisis. There is the war. There is there is a recession, etc., etc. But still, my point is that from industry point of view, we would need to know a bit when these are happening, in order to really make large investments and so forth, and then. There is the politically made market, and that's for fuels. Other ones are not yet happening. There are some pilots going on, but when you think about pilot, if you have a pilot, it's at least 5 years from now when it's industrial. So the time scales for having this happening are long, and they are kind of now running away from what we thought. But I'm convinced that they will be there. But there's a lot of work to be done in order to make this energy efficient, and there's a lot of innovations to be made here. So I wish you will do that. Oh no, this is a wrong version, but in any case, I've ensured the numbers. So this was actually the only number that was missing, and I have to say that it was double the one for e-methanol production. In any case, the hydrogen production is the one when you try to make the end products. The hydrogen production is the one that really using the electricity. So if that could be reduced, the overall electricity production would of course be lower. And then e-methanol, in order to make 1 ton of it, you would need 12 megawatt hours of electricity. And if all Metsä Group's bio-CO2 was converted to e-methanol, we would require all electricity that was produced in Finland now. So some work needs to be done. I'm sure it will happen, but it will take some time, and I trust that there will be new inventions happening. So in order, just a summary of what I've told. So circular economy, bio-based CO2 is one building block of it. And we are convinced that there will be new chemical industry based on this one. Well, then hydrogen economy in general needs a lot of renewable electricity. It is considered as a storage of electricity, renewable electricity, but it also needs a lot of investments, and kind of these things needs to be done stepwise, starting small, thinking about different routes, and kind of letting different kind of technologies to develop. And there is quite a lot of way to go in order to be competitive with kind of non-politically regulated products, but it will happen in a decade or two that there will be enough innovations in technologies. Thank you.
Okay, thank you very much for having the opportunity to talk about biotechnology, and also to talk about some of the research going on in my group. So the topic is biotechnology with methanogenic archaea. And what I will first talk about is what can be done with wild-type methanogens. So these are microbes as they are found in nature, so not genetically modified. Then I will spend a little bit of time with the biochemistry of CO2 reduction. And then in point 3, I will talk about the production of multi-carbon products via genetically modified methanogens. And then towards the end, I will present a case study about e-propane, so one of the newest projects in my group. Okay, so first about natural methanogens. So these are used, for example, in the Finnish startup Q-Power. And so what they do, they convert CO2 and 4 hydrogens to methane. And this way you can basically valorize the CO2. And it is also utilization of excess renewable energy. And then the methane formed can be fed into the gas grid. And then what has to be mentioned here in red is here we have already a quite high technology readiness level of this process. And so now I would like to spend a little bit time on the biochemistry. So you need 4 hydrogens to convert the CO2 to methane. So this is displayed here. And so this would be the pathway with 1 carbon intermediates, so formic acid, formaldehyde, methanol. And then these steps are differently difficult. So the first step, the reduction of CO2, is more challenging and endergonic, and then the last steps are a bit more exergonic. So this is the chemical way, and now on the left side, I show to you how this is done inside the microbes. So inside the microbes, we don't use hydrogen directly, but we use these redox cofactors, which are in this blue box. And then what nature is able to do, indicated with this red star, is a process called flavin-based electron bifurcation. So basically 2 hydrogens are going in, and then they're split into a very low potential electron donor called ferredoxin and a higher potential electron donor. And then so this helps balancing the pathways and accomplishing these difficult tasks. So the conclusions here from the biochemistry is especially the second point, that endergonic and exergonic steps can be coupled. And then what's also special about these microbes is that CO2 is actually the food of the microbes. So organisms that you are familiar, like humans or yeast, they usually produce CO2, and so these microbes are sort of doing the reverse. They are eating CO2 and hydrogen, and then they're making a fuel out of it. And because CO2 is their carbon source, it means that more than 95% of the CO2 that goes in will come out as the product methane. And so this process is reversible because the electrons are so well balanced, and it's happening close to the thermodynamic equilibrium. And now moving to multi-carbon products. So my research topic is CO2 valorization with biochemistry, and the goal is to make compounds with more than 1 carbon. And when you want to do that, then the question is, do you have carbon monoxide available or not? And if you have carbon monoxide available, there is a quite nice process by the company Lanzatech where you can produce alcohols. So here shown on the top. But now what I want to address is the situation where we just have CO2 and hydrogen, and can we produce something useful out of that? And my approach to take these methanogens. And so to produce multi-carbon products, we actually rely partly on the native metabolism. So in this purple box, you have the CDH enzyme, and so this enzyme actually makes the carbon-carbon bond. So it takes a methyl group and another CO2 and forms acetyl-CoA. And so this is where some of the pathway goes. And now, to use them efficiently, we need to avoid methane formation. And 3 years ago, there was a breakthrough that we have a methanogen that does not make methane anymore. So this methanogen basically combines 2 CO2, and then it forms acetate as a product. So this is sort of a proof of concept that methanogens can be used for things other than methane. And so what I want to do, I want to go this route, and then we should produce something that's more valuable than acetate. And so for that, we need additional reactions to be implemented, and for that, we need synthetic biology, so that microbes can be cell factories, and for that, we need to insert genes into the microbe. And so basically, the steps are shown on the left. So how it works is we insert genes into the microbe, and inside the microbe, these genes are expressed to enzymes, and the enzymes are the actual catalysts or the reaction. So basically, for every gene that we introduce, we can have a new reaction happening inside the microbe. And so in my group, we developed some advanced tools to better bring in DNA into the microbes. And so as a proof of concept study, together with Paolo Jochten, we are producing butyrate with methanogens. And so for this, we actually produce 2 times this acetyl-CoA, the C2 compound. And then what is shown in purple is basically synthetic biology. So these are additional pathways that we engineer in order to produce butyrate by this microbes. And then just some more, maybe a bit a detail about biotechnology. We can actually control the fluxes. So we have so-called promoters. They define how much of the enzymes are formed. So we have a promoter library. We can start controlling these fluxes. But now I would like to move to something that has an even higher relevance. So as I said, the difficulty is that without carbon monoxide, the product scope is very limited. But this slide basically summarizes what is thermodynamically possible. So the first cases, acetate and butyrate, I've discussed. Methanogens make methane. But then here in yellow is what I think a very interesting case, that actually propane production is thermodynamically feasible. So the question that we ask is, can we convince methanogens to produce propane instead of methane? And we obtained some funding from Business Finland. And so this is how the overall value chain would look like. So in this box is the e-propane process that we will convert hydrogen and CO2 to propane. And propane is interesting because it's already nowadays dehydrogenated to propylene, and then with propylene you can make polymers and C-free chemicals. So for this reason, Borealis and Neste are very interested in this project. So then the question comes, how can we reprogram the microbes to make propane? Because this is not very common. But then if you look into nature, I told you that methane formation is reversible. So there are microbes that are actually doing the reverse reaction. There's microbes that convert methane to CO2. And what you have in the green box, there is microbes that convert propane to CO2. And so in nature, they do that with sulfate as the electron acceptor. And basically, the goal in my group is that we want to elucidate those pathways. And once we find out how propane is converted to CO2, we take the same enzymes and we insert them into a methanogen and then trying to produce propane. And now, maybe it's a little bit complicated, but I have introduced before this CDH enzyme that goes to acetyl-CoA and butyrate formation. And what's shown on this slide is how I believe that these microbes are oxidizing propane. This is now shown in the opposite direction. And what's interesting that we have a second, in those microbes, we have two versions of this CDH enzyme. So the normal CDH enzyme converts the methyl group and the CO2 to the acetyl group. And then the hypothesis is that this second, a bit strange version of the CDH enzyme is actually able to produce a propyl group. And then this propyl group would finally go towards propane. And so what we are currently doing, we are testing this, this hypothesis. So we are expressing individually this CDH1 and this CDH2 versions, and then we test their ability to process acyl-CoA thioesters. And here is an in vitro assay. So we test an acyl transferase assay, but basically the conclusion is that we compare the purple normal enzyme variant and then this green variant that's from the environmental microbe. And what we find is that the normal variant is doing the C1 reaction, producing acetyl-CoA. And then what we find with this special variant, that this one can actually accept butyryl and valeroyl-CoA very well. And that basically supports this hypothesis that with this enzyme we can generate a propyl group. And then the next step is to introduce all of those enzymes or the genes for the enzymes into a methanogen and then allow for propane production. So this is again sort of the value chain. And now what needs to be noted is that we have an existing e-methane process that has already a high technology readiness level. And then the concept is if we have a microbe that produces propane, we can actually implement this microbe in the same setup and with the same type of engineering. So here I've summarized the take-home messages. So e-methane is ongoing and has a high technology readiness level. The biochemistry is reversible, and biology has learned to couple endergonic and exergonic steps. And then point 3, so with biotechnology, we can basically genetically program microbes to do what we want them to do. And then in terms of the e-propane, propane is thermodynamically feasible. And then the good thing is that if you would have renewable propane, it would feed into existing infrastructures and it would not be so much investment costs for the chemical industry. And then as mentioned at the end, if you would have such strain, that can be quite easily implemented because the e-methane process has already a high readiness level, and it would be in a similar way a gas-to-gas fermentation process. So with that, I would like to acknowledge also my group and some funding. We have a very well-equipped laboratory at Aalto to work with a lot of hydrogen and CO2 and in the absence of oxygen. Thank you.
So this could be a little bit weird. It's actually quite normal for me. It's the talk I usually give. But about sort of our research and how we translated some of it into nearly commercial scale activity. I say it's weird because most academic audiences aren't used to the concept of commercialization, but this conference is actually quite an exception, I have to say. So maybe you're going to think this is quite normal, which would be a nice relief. But there's a picture of me with an ionic liquid in Antarctica. And so I have never been an explorer, but that was the first time anyone took an ionic liquid to Antarctica. And since it is illegal to take anything into Antarctica, that is a picture of me violating approximately 37 international treaties. Luckily, I did not get arrested yet. But anyway, there it is. That is a really nice shirt, too, I have to say. Okay. So I have a lot of jobs, as was mentioned. So I'm a professor at Imperial College, and I'm one of the people who runs the National Bioenergy Hub. I'm responsible for the chemicals and materials part, and somebody else does all the burning of biomass because I really can't stomach that idea. And also, I have a similar role in vaccine manufacturing, which we will not talk about today. Drug delivery, it's really not that interesting. It sounds like it, but it's not. And I have founded, my group has founded 9 companies. I'm technically a co-founder 8 times, but I don't claim Rumify because I don't really do anything for them. And when it was 4 companies, I used to give slides on each of them. And then when it was 7 companies, I'd give like a 1-line description and talk it out. But now I just put it up there and you can read it if you like. But we don't really have time to go through them all. 3 of them, maybe 4, 3.5, work in biorefining, which is quite interesting. But 8 of the 9 came from research that was done in my group directly. And the 9th one was one that we did sort of with the company so they could form the basis for their commercialization. So I have a lot of experience in trying to do this sort of tech transfer activity. And when I started trying to do this, which was in 2010, and we finally spun out our first company in 2017, it was unusual. And over time, it has become much more accepted, and in fact now encouraged, and I would say even perhaps a little over-encouraged at times, to try and spin out companies out of universities. And one of the jobs of a spin-out is to generate, what we like to say, sort of establish the brand, which is another word for saying generate a lot of PR. And so we do a lot of things that get in the news. There's a picture on the upper left of my co-founder, Ida, and I. We have a company that recycles textiles. Technically, we recycle textile fibers, but we always say we recycle textile dyes because it's very fancy. Very, very pretty stuff. That's us accepting the H&M Global Change Award 2 years ago in Stockholm. which was quite fun. That's a solid glass ball. I almost dropped it on my foot because I thought it was hollow, and they handed it to me. In the upper right is a picture of, this is my favorite picture. So it's the three founders of Lixia, Florence, who's on your right, Aggie, who's in the middle, and Jason, who's on your... And they cut me out of the picture. So Scientific American, when they ran the picture, we sent them the picture with all three of us, and they put the two of us in the picture. I'll show you one later on where they couldn't cut me out. Lixia was named one of the top 10 emerging technologies in 2019 by Scientific American. We were the emerging technology for the category of bioplastics, which was very exciting. Lixia does not make bioplastics, but that's okay. We'll take it. We make packaging, but not plastics. I have a company, Nanomox. This was an article in a UK newspaper about Nanomox's steel recycling. It's been cut off. And I make a lot of jokes about the one on the lower right, but actually in this audience, pretty much everybody but me can read that headline. But that was when Lixia opened their pilot plant in farmland. We were interviewed, Aggie and I, on the local news about it. I have been interviewed in 6 different languages, which is quite impressive since I only speak 1. But you can find on the internet interviews with me in a lot of different countries on different topics. And the reason that I think it's important to do translation or entrepreneurship or trying to take science out of the laboratory, it's not necessarily about getting your technology out there. That's great. It's great for me. I like to see it. Positive change on the world, I think, is important. But even if all of those companies fail, and statistically only one of them is going to make it, but even if they all failed, what we have done is create a suite of founder CEOs. So we've turned graduate students into CEOs. And honestly, I thought being a professor was a difficult job, but running a startup company is an impossible job because you have to do everything. And so all of a sudden I have these graduate students who are great in the laboratory, and they have turned into people who can do everything from pitch to a room full of investors, run small-scale pilot plants, or possibly do the accounts and taxes for the company. I mean, it's incredible, the list of things that you have to do. Clementine often tells me that she spends most of her time arbitrating disputes over who stole whose lunch. And there's a picture of Clementine in the upper right. She founded Orja Technologies, which is a solar power company. They do solar mini-grids in India for communities, farming communities that don't have access to electricity. Clementine has had a documentary made about her. She's been profiled in 14 different newspapers. She was named MIT's Innovator of the Year a couple of years ago and Chemistry World's Innovator of the Year. She has no ties to MIT, but they were so impressed with what she's done. And when the Times of India listed the 100 most important people in UK-India relations, and of course UK and India have a very long history, she was listed number 38. Number 1 was Queen Elizabeth. She was 38th on that list. She was at the time a robust 26 years old. Absolutely incredible what she's done. And Orja's had a huge impact. They just celebrated 1 megawatt of capacity installed. It's quite impressive. I think they brought electricity to 14,000 people who didn't have it before. In the middle, there's a picture of Ida, so my co-founder in the textile recycling company. She was interviewed by a British newspaper about why women would possibly ever want to be a chemical engineer. And Ida has a fantastic backstory, which is quite tragic at the moment. She's a Palestinian refugee. Her family's from Gaza, in fact. So she's been running dye recycle with the background of a war in her home. But she's an absolutely incredible figure. Worked in oil and gas for a couple of years in Qatar and decided that she didn't want to ruin the world, but she wanted to save it. And there's a picture on the lower right of Florence, my co-founder of Lixia, who accepted IChemE Global Award from Warwick Davis. She had no idea who he was, but I did. I said, it's Warwick Davis. He was an Ewok. I mean, that's impressive. It's Willow. I took that picture. I'm very proud of it. She gave an interview about why she decided to stop running Lixia, her own startup company. And at some point, she decided she liked the technology more than the business. And so she stepped back, and now she's actually left the company. But quite an interesting story. Okay. We'll come back to Lixia in a moment. I don't want to give too much technical detail. Ionic liquids raise a lot of emotions in people, I find. And the ionic liquids that I use are ionic liquids in name only, so to speak. And I'll explain what I mean by that in a moment. Historically, what ionic liquids have been considered are liquid salts. And they have incredibly complicated structures. There's a picture of it at the top. Everybody, for most of the 1990s and early 2000s, kept touting them as green solvents. I have to say they're not especially green in terms of solvents. If you look at them as a material, they're actually not all that sustainable. If you look at how you use them, then it becomes more of a question. And I'll give a very brief example of what we did that in a moment. The reason that people got excited about ionic liquids is because you make them do anything. And they are kind of miraculous in that sense. You can make an ionic liquid that will do absolutely anything. So they're very, very flexible. But they have some drawbacks. And I'll explain what those are and how we overcame them. I work in biomass fractionation for the most part. We do have some activity on making some bio-based products also. But this is my main love interest in the field. And the purpose of fractionation is usually to do some specific job, either to purify cellulose for materials applications, which is what Lixia does, or what our research was originally on, which was to try and activate enzymes to make cellulosic sugars, ostensibly for biofuels. And the reason people liked ionic liquids is because they work really well. The US Department of Energy did a massive screening of fractionation. They did different fractionation technologies at 4 or 6 or something different labs, and they tested 47 feedstocks. And the ionic liquid was the best performing solvent on all 47 feedstocks. So they got the highest enzyme activity every single time. So they work really, really, really well at producing pulps that have a high accessibility for cellulases. However, they are ridiculously expensive. And so while on a performance or effectiveness criteria they look great, if you look at a sort of a cost efficiency perspective, not so good. And so how do you balance those two? I'm an engineer, so I tried to look at this a little bit I always try to look at problems backwards. So engineers like to work backwards. Let's start at the end and go back to the beginning. And ionic liquids are great at dissolving cellulose. This is what got everybody excited, is that they dissolve cellulose. And you put in cellulose that's completely crystalline, and you get out cellulose that's completely amorphous. The ionic liquids that are capable of dissolving cellulose are very, very expensive because they have complicated structures like the ions I show on the right. And also they're not very stable, which as an engineer, that's a bit silly. Why would you want a solvent that decomposes? That's the last thing that you want. This is really cool because cellulose is hard to dissolve. And so it's quite neat that you can dissolve. Emium acetate, the one on the lower right, will dissolve about 25 weight% cellulose at 80 degrees. That's a lot of cellulose. If you want to make sugars, I don't know why you would need to dissolve cellulose. And so, since getting cellulose into solution requires extensive drying, so it's really expensive, a lot of energy usage, could you just dissolve lignin? And so could you run sort of an organosolve pulping process on biomass with an ionic liquid? And the answer is yes. And so this is what I decided to call ionosolve. I'm not very creative, so I said, we're doing organosolve pulping with ionic liquids. Let's call it ionosolve, right? And it is much more efficient, and you can keep water in the solvent because you don't need the cellulose to dissolve. In fact, you have to have some water in the solvent. And this meant that all we need now is a solvent that will dissolve lignin, which is not native lignin. They're technical lignins, Orlando. I mean, I'm not, I'll have to put the air quotes around it. But you can now design a solvent that will be extremely efficient at lignin extraction. And I can show, there's some pulps in the sort of lower middle. So this was our input biomass, and that is unbleached cellulose pulp that we got out. In fact, that sample right there is 98% glucan, 1% lignin, and 1% ash. And that was what we got out from, I can't remember, wheat straw, I think. And you can use a lot of different ions for this. The key reason that this became a commercial activity had nothing to do with the science, actually. It had to do with a techno-economic analysis that I did in 2014. I said, how would you make an ionic liquid that wasn't expensive? Since they work great, but they cost too much, how do we make them not cost too much? And again, I'm not very creative, so I said, what's the cheapest, absolutely cheapest chemical in the world? It's not water, it's sulfuric acid. Nothing is cheaper than sulfuric acid. It's a waste product, it's great. And so we made an ionic liquid that's half amine and half sulfuric acid. It's an acid-base complex, so you just mix the amine with the sulfuric acid, and the cost of the solvent is almost exactly half the cost of the amine. And so we ended up with these solvents that sort of, and I apologize I didn't put this in euros, but I can't do, the markets are moving up and down too fast these days. I can't do any currency conversions. But they're about 50 cents a kilo, somewhere between 50 cents and $1 a kilo. So somewhere between, say, ethanol and toluene on a cost scale. The ionic liquids that dissolve cellulose are about $20 a kilo. That's not a solvent. That's an end product. And we did an LCA. I won't go into details on the LCA. And what we found was about what I said at the beginning. If you compared the ionic liquid to an organic solvent, it's less sustainable as a material, but is more sustainable in the process. And so that's actually quite important. It isn't necessarily that the material is green, so you don't have a green solvent, but we do have a green process. And that's because the energy use is substantially lower. And I do think that a lot of this field has been colored by the initial application in fuel cells. Everybody was making ionic liquids to make electrolytes for fuel cells, and they're incredibly expensive chemicals, but they can afford to be. If you want to do large-scale processing, you need something cheaper. And sadly, I don't have time to go into all the details, but it does work really well. And initially, we were making cellulose. There's some pictures up the top of some of our cellulose pulps, and there's a film of MCC or nanocellulose, somewhere in between the two. I think it was NCFs that we have on the right-hand side. We did some lignin fractionation. We recover the lignin from the solvent by adding a little bit of water. And if you add a little tiny bit of water, you get the big lignins out first, and then you add more and you get them smaller. And so you can do a molecular weight shift. On the lignins, you don't have to do any redissolution. We made some food-grade solutions to ferment into protein directly, so you can use food-grade solvents for that. They're actually improve the fermentation yield. Get pretty high glucan recoveries, very high sugar yields. We got published a paper, we got 100% glucose release from pine, so it's the first time somebody had gotten 100% from a softwood, at least using a solvent. And the fermentation rates are identical to glucose, so to food glucose, sorry. So the sort of sugar aspects are really, really good. I was more fascinated by the materials because initially we were getting sort of 90 to 95% cellulose in our pulps, and as I said, we've pushed it up. We have one, I had a picture on the previous slide. In the upper right, so we had a pulp that was had 0.3% lignin that came out of the reactor. So you can make extremely pure cellulose. It's an acidic salt, and so you have a trade-off between fiber length and lignin content. But you can sort of choose where on that spectrum you are. Because they're salts, you have no danger of evaporative losses, and so the recovery rate is really, really high. I did a study in the laboratory where we recycled the salt 10 times, and that took us about 1.5 years to do because it was really, really difficult. And so when Lixia ran their pilot plant, which I'll talk about briefly in a moment, but they've been running the same solvent in that plant since May of 2022, so 3 years now. They've been running the same solvent in that plant for 3 years. It's pretty good. Every 6 months they send me a sample to see if there's any evidence of decomposition, but so far nothing. So it's quite good. And we did a lot of economic analysis because we're getting these nice, beautiful, beautiful pulps. And we published a paper back in, I forget, 2017, showing that at scale, which was about 500,000 tons, you could produce glucose slightly lower price than food-grade glucose. So it is cost competitive with cane syrup. I'll have a graph at the end, which we probably won't have time for, but showing how that has evolved over time. Because at the time, energy prices were low, and sugar price is dominated by fertilizer price. So whatever the gas price is, that tells you how much cane syrup costs. And so at the time, we were about 90% of the selling price of cane syrup. 2 years ago, when the energy prices were extremely high, we were 1/4 the cost of cane syrup. So it does actually depend on when you look exactly. Anyway, the biggest selling point that we had from a technical point of view was that you could put in anything into this, and we did some studies on mixed feedstocks showing that we could get 99% of the sugars out, even if both two types of biomass were in the reactor at the same time, same conditions, same time, right? So they can fractionate together. You can go to quite high solids loadings. You lose a little bit of sugar if you go to higher solids loadings, but 50% solids in the reactor, and you still get a pretty decent result. So if you're making biofuels or fermentation products, you can have a really, really efficient process because you can go to really high solids loadings, and you can sort of drive the economics by minimizing disruption. Orlando talked about this in the first talk. It's like nobody ever talks about this, but this is a study we did a long time ago. It's about 10 years ago. But I decided that if it works on anything, why don't we use the most disgusting, dirty, degraded samples of wood we can? So this is construction waste. It's chromated copper arsenic treated wood. So it's got chromium, copper, and arsenic in it. It's about 0.5% copper, 1% chromium, and 1% arsenic by mass in the wood sample. And this is, of course, used in construction so that it will never rot. CCA was banned in 1995 in the European Union, but of course that means all the buildings we tear down have got this in it. The ones we put up don't. We only put copper in it now. But ionic liquids, of course, as I said, fuel cell electrolytes, they're awesome. It's complexing metals, and you can sort of electrodeposit them right out. And so we get effectively quantitative removal of transition metals and arsenic out of the salt. And this is quite unusual. And it made a really strong economic case for doing this. And so it's a very young picture of me at the founding of Lixea in 2017. So that's the three founders, the same three of us that were 2/3 in that picture at the beginning, when we built a company off this, because this was a nice thing. Now, the last few minutes, I asked Lixea's CEO, Christina, I said, I'm going to be talking at this conference in Finland, and I want to talk about Lixea's demo plant, because it was just announced. Can you send me 1 or 2 slides? And she sent me the entire investor pitch deck. So, these aren't my slides. They've got transitions in them, and I don't know where they are. It's designed for investors, so if anybody's got a few million euros to spare, let me know afterwards. I can hook you up. It's a great investment. But the reason I left it in more or less intact, even though we'll have time to go through it, these are my slides. Well, these are Lixea's slides. Look at that. That's an academic making a PowerPoint slide. It's not bad. Oh, look at that with the thing and the lake. We own this picture. I mean, it's really nice. That logo is really complicated. This cost us a lot of money. But absolutely beautiful. I mean, look at these things. I mean, oh my God, look at this. This is like, I couldn't do this. First of all, it's too much text. I don't really like that. But this is the investor pitch deck. So this is like the most positive view of the company and what we're doing right now. But it's all about things that are very familiar in a meeting like this, right? The bio-based material market is growing. This is an opportunity. And I do think that it's important to remember this is an opportunity. Lixea has done some crazy things for a company that's only been running at pilot scale for 3 years. They've worked with 200 different partners on producing end products because they make intermediates. The big challenge is to figure out what could be made from their intermediates. This is sort of the exciting part of the company, and it's a little bit unknown what is and isn't going to happen. Again, we have to go through the transitions because I don't know where they are. But it's the same message underneath it that I was just talking about. We can process anything. So we have a process that is capable of taking in any kind of feedstock. And I think they've run 13 different feedstocks in the pilot plant. I don't know how many we've done in the academic lab. I stopped counting at 60. I used to have a list. It was really long, and some of them were extremely strange. We've processed asphalt in this solvent to pull things out. It's quite good. That solvent will take anything out of anything. That's really, really good. At the center, though, is the same things I talked about, right? Driven by cost and performance. Those are our big keys. We're trying to keep the cost low. We're trying to keep the energy usage low. We're trying to keep the inputs flexible. And so it is kind of the same message delivered in a slightly different way. Now, Lixea makes 3 products. They make cellulose, lignin, and furfural. And those are the 3 things that they are sending out. So like I said, intermediates that are going into other people's products. The big advantage that we have is the purity. The cellulose contains virtually nothing but cellulose. their first product, I think, is dissolving pulp. The lignin is extremely pure because there's no sugars in it. The furfural is extremely pure, and actually, weirdly, we get high yields of furfural because the acidic solvent does a reasonably good kinetic job of converting pentoses to furfural. So it's quite nice that you can get 3 products out with 1 fractionation step and 2 separation steps. Now, the only reason I put this up here is to talk about the demo plant. So I don't even know what the slide says, so I'm not going to go through it. But what are they doing? So since they're flexible on inputs and outputs, they have a lot of certain different target plants that they're building. The first one, which is L1X, which was just announced, and is supposed to be built in 2027, is going to make material products. So they're going to make cellulosic materials. Dissolving pulp is probably going to be the most prominent one. And then the next plant that they build, which will probably be in, well, they're saying Canada, but somewhere in North America. Originally it was the US, but it was sort of shifted to Canada. I don't know why, don't ask me. Is to make bioethanol. And these are sort of the things that we're getting a lot of market pull on at the moment. They also have plans for a biogas plant that will be in Scandinavia. I can't remember, I think it's in Finland actually. And a recycling plant for Western Europe. And so this is sort of the first 4 plants they're planning to build. The funding is secured for the first one, and we'll sort of see about the ones that follow on after that. But that first plant's going to be the blueprint for what's going to happen. And the reason that they're so keen on this is because because the economics look very good. And so oddly enough, I was the one that set the scale on the demo plant, and I said, well, set it at MPV 0. And so basically it will break even. But our CEO is so good at securing concessions from national governments that actually I think we might turn a profit. I don't know what you do with profit in companies. I only do startups. Startups don't make money. So it'll be interesting to see, but quite exciting. And so when Lixia moves to the next scale, we ought to be able to do quite well. L1X is going to be approximately 25,000 ton capacity, built in Slovakia and designed for wheat straw. But this is really the big thing, right? I mentioned the cost. I'm not sure I really believe that dot should be so high. When I made this graph, I put us below kraft pulp because I'm not sure I'm completely convinced by that. But this is really our key selling point, is it's a very cheap process. We don't use very much energy to do this separation. The solvent does most of the work for us, so we don't have to put in a lot of thermal energy to do it. There was one more thing I wanted to mention. Yes, so this was the last thing I wanted to mention, was the two fancy pictures. So we've been operating, as I said, for 3 years, a pilot plant in Värmland in Sweden. Quite a pretty site. I love these pictures. This is when it was brand new, so you can see how clean the floor is. It's now completely sticky and covered in lignin, but that's okay. Once upon a time, it was absolutely beautiful. And that process has been operating for 3 years. And the solvent so far has held up. It took about 2 years before we started seeing impurities in the recycle stream, actually. And the 2 products that they've gotten the most traction on are dissolving pulp, because of the high cellulose purity and the removal of hemicellulose, and hard carbons, actually, for batteries from lignin. And oddly enough, there is enough demand for 10,000 tons of lignin from the demo plant. I was quite surprised, but they're going to be able to sell it all. That, I think, is the end. Oh, I was going to show you, no, I don't know what's going on here. I was going to show you the picture. Where is it? There it is. So there's the first picture of our demo plant. I'm so happy to see that. It's obviously going to be bigger than that. That's just a cartoon, but it's quite nice. And so we secured a 30 million euro grant, 20 million euro grant from the EIC to help fund part of that 60 million euro project. And that's it from me. Thank you.
Thank you so much, Jason. That was very exciting, and congratulations.
Thank you.
Do we have questions for Jason? Yes.
Hi, thank you for the presentation. I'm curious about the properties of the lignins that you extract using the ionosolve process? Like, how are they different from the conventional processes, and like, for example, in terms of molecular weight and functionality? Yep.
It's a good question. It's a complicated question. I mean, it's lignin. It's a complicated question to answer. They're low molecular weight, so they're a couple thousand daltons in weight. And depending on how you fractionate it, you can get some really small fractions that we get out, which are about 500, so maybe tetramers, up to some large fractions that are several thousand daltons that come out. In terms of functionality, they're very reactive, which is quite nice. So they're very good for making resins. They're excellent for carbonization. They don't have many ether bonds intact, but they aren't very cross-linked. So they're somewhat in between, say, organosolved lignin, which has a lot of ether bonds, we don't, or lignin first, which is completely broken down. They're a little bit larger than that. And kraft pulp, so they're not highly condensed. So they're still quite soluble. So they're good for some applications, especially applications where you want to functionalize the lignin. They're not ideally placed if you want to make small molecules out of them, because they do have a little bit of cross-linking that's happening, a little condensation.
Yes, Orlando.
Thank you so much, Jason. And with time, I'm getting to know more and more about all your developments, and it's really great. But I have a question, maybe more philosophical. Right? So, you know, as a professor, of course, we are not really made to start companies, right? But obviously, you have cracked the nut, and you have been very successful in doing that. And I just want to ask, maybe if you can give us advice. What is that you do different? How do you determine that an option that you can publish in a paper have an opportunity for a startup? So what is that what is your mental process in doing this?
I get this question a lot. I actually don't know, to be honest. It is a great question. I mean, some of the reason that we've done in my group, or me personally, that we've done so many of these is because I think, partially because I'm an engineer, I think about applications. So we're always looking at the start, does this have potential to be deployable? And I usually focus on economics and scale. Those two things. Can we do it at a proper scale? And you have to have a reasonable market understanding to make that determination. And so that, I'm sorry to say, can only come from experience. So you have a lot of experience perhaps in that market, right? Then it's great. If you don't, then you really are flying blind. And this is where you get a lot of people who think they can start a company but can't. I think the other thing, I recognize my limitations. I can't run a company. I am way too much of an academic. We used to do the pitches for Lixea, and Florence would do the pitch and I'd do the Q&A. And we came out of a Q&A one time and she was fuming angry. And I said to her, what? I thought that went well. And she looked at me, she said, you are such an academic. I was like, what do you mean? She said, you said this, they asked the question, and you said, oh, it could be this, it could be this. She said, the answer was no. You talked for 30 seconds, and the answer was no. So you have to get over that, right? And you have to recognize that it is a significantly different skill set. But I think the biggest hurdle that I've had to overcome is recognizing that in a business, a startup success is determined by the business, not the technology. Nobody cares about the technology. Lixea can make really pure cellulose. Okay, that's it. How do we do it? Did you see anything in that pitch deck that said how we did it? No, because nobody cares. They care about the product and its market. They do not care about how you got from A to B. And so you have to let all of that go. And if you can let all of that go, you can have a great startup. But if you're going to be precious about how awesome your technology is, nobody's going to invest in it. Best I can offer.
Excellent. Thank you so much, Jason. Thank you.
Thank you so much for having me today. I'm very honored to be back home. Thank you, Monika and Tekla, for providing this opportunity. As Nina said, I will talk today a little bit about how to use polymer assemblies, mainly cellulose, into alleviating some critical environmental issues, and I want to share with you how I ended up doing this kind of work at Auburn University. So first I would like to give you a little background on myself. My funny accent comes from very south. I'm a southern girl. I grew up in Argentina, and I fell in love with the pulp and paper industry back home when I was doing my bachelor. And then in that journey, work a little bit for the Argentinian government, getting ready to join Orlando's troops at NC State back in the times. So I started my PhD in pulp and paper engineering, and with the decline of the industry, that program became the program on forest biomaterials, where I started working with nanocellulose. And in the way, as everybody else in the group of Orlando, landed at Monika's and Janne's group for have a wonderful year in Aalto University, where I had the fortune to meet also our VTT colleagues, and Tekla recruiting me to VTT, where I came for a postdoc of a year, and then she kept me captive for like 5 very long winters. In 2016, I moved to Auburn because I decided that the weather was not coping with my Argentinian character, and I started a tenure track position at Auburn University in the college of, back in the time it was a School of Forestry and Wildlife Sciences, which was quite an interesting story, because I will tell you that this is part of the why I ended up working on environmental issues with material science as well. So I recently, like about 2 weeks ago, became a professor at Auburn University, and as of August 1st, I am moving to Clemson, South Carolina, where I will be the director of the Good Utilization and Design Institute, with an appointment, shared appointment with, between forestry and material science engineering. And part of this visit is very timely, as it was planned by Tekla as well, to see how can we coordinate efforts and how can we help the forest industry in the southeast of the United States as well, and try to bring the Boreal Alliance back down south, where there is a very large amount of forest biomass as well. So if you are familiar with the United States landscape, so this is how the forest land in the United States look like. The bright yellow, bright green that you see on the south or the west, the east coast, is mainly privately owned. So in the state of Alabama, where I'm currently at Auburn, the private sector owns 98% of the forest land. And back then, when I came to Auburn, there was already this trend that we continued to see, with opportunities for opportunities given by the dramatic amount of mill closing in the states, mainly where all this privately owned forest is, and those jobs that they were lost by, and plenty of community and for workforce development opportunities with innovation as well. So many opportunities, certainly with the environmental issues, decreasing greenhouse gases emissions, and replacing limited resources for sustainable resources. However, we kind of like trying to change the speech a little bit, and while we are doing environmentally good things with the using of biomass and replacing fossil-based resources, we also try or have the opportunity to increase national security and decrease the dependence on foreign resources, as well as increasing internal markets, such as agriculture and forestry. So I don't really need to tell you what are the opportunities that this bring, but certainly with meaningful partnerships with Finland and our colleagues in Canada, it's really a golden opportunity. Also, I thought, as a Finn moving to the south, when I went in the first Trump administration. So certainly the area of biomaterials is having a hype, particularly not in the United States right now, but I really believe that the sustainable needs in product development can meet these resources supply and oversupply of resources in the southeast. Also, we can really use forest or bio-based materials to impact food or improve food security and environmental health as well. And for that we need meaningful partnerships, and hopefully that they will help us to remove those barriers for commercialization. So back then when I moved there, loyal to the legacy of Orlando and Tekla's influence on my work, I was ready to eat it up in Auburn by implementing this like super innovative approach, trying to understand the interfacial and surface science of different raw materials and bio-based resources that we had in the Southeast, and trying to understand the structure-function relationship to enhance and advance innovation in forest products. So what really happened was that I was, as you probably remember, I was there in the School of Forestry and Wildlife. I am not either wildlife or a forester. I wear like heels all day, so I know nothing about the forest management. So I studied like, I made a really different reality in terms of product development that was at VTT those 5 years at work here in Finland, and trying to implement this transition from housing, communication, and transportation, those like very traditional uses of biomass, to new markets and share the opportunities that exist with these bio-based materials. It was a rather challenging speech to sell, so to speak. So you are very well aware with when life gives you lemon. Well, I drank a lot of lemonade the first 3 years at Auburn University. So what I decided to do was to try to identify those issues that they were locally alarming within my colleagues in wildlife and forestry, and try to find sustainable solutions for some of those from a material science point of view. And here you see a very busy slide, but I will share with you some of them, particularly Alabama being an agriculture state, very heavy on agriculture practices. I decided to go and focus on some control release materials and how can we use these polysaccharide assemblies for control release of agri-chemicals and try to decrease the impact on the environment, as well as trying to focus on water remediation issues, control or reducing of volatile organic compounds in the forest industry with their very traditional views of forest industry, the speech needs to change. I think that this is a really powerful message to those of you who may be starting a new academic career and trying to like adapting means a lot when you are in a new environment, for sure. So today I will show you a couple of the examples of things that we've been working on and hopefully sparking your interest to discuss potential collaboration. So this is the work that Diego started. Diego Gomez Maldonado is now a faculty member at Texas Tech. And we started looking into lignocellulose prills or hydrogels beads for encapsulating agri-chemicals, both pesticides and fertilizers, and trying to see if we could use those to, again, try to alleviate issues such as food security, as well as environmental impact, and also the water of the quality, the water quality in the area. So the first thing that we started to look into was like trying to dissolve and regenerate cellulose in the form of beads, which is nothing really novel. But with the approach that we took was trying to figure out how could we use any biomass that we had available. Because again, the availability of resources was rather limited for a few years. So we were trying to figure it out if there was an easier way to process this biomass and if we could use alternative feedstocks to produce these lightweight beads. So we decided to go the route of using mechanical fibrillation of cellulose instead of dissolving pulp, and we had this hypothesis that the high shear treatment of fibers and cellulose or lignocellulosic materials with a supermass colloidal through fibrillation will allow us to reduce the degree of polymerization enough that we could dissolve the cellulose and regenerate it in beads and create an alternative and easier route of creating these beads. Indeed, we were able to decrease that degree of polymerization and reach about 80% of solubility. And we started investigating all kinds of sources of biomass to produce these prills and try to take advantage of remaining extra chemicals that they were in the cell wall of the materials that we use. We use oats, hulls from soybean, and from anything that we could get our hands on, pecans, peaches, pits and all kind of crazy things. Hop from brewing, spent brewing materials, and as well as lignin-containing fibers as well. So two ways that we were trying to investigate this material in terms of applications. One of them was in the area of food security, as I mentioned. So as we all know, the population growth is very alarming, and by the rate of growing our population, we will have to really come up with very innovative solutions to create more food, or else to increase the yield of our crops. You can see here some data from the FAO, from FAO. The yield of crops have been decreasing dramatically over the last 4 decades, and whether we change our agriculture in a dramatic way, we will not be able to feed our next generations. So nano-enabled precision agriculture has been taking up and a lot of attention, at least in the United States, in terms of using these nanoparticles, mainly inorganic nanoparticles, to improve yields, crops, and decreasing the leaching of some of these agrochemicals in the environment. So we decided to go this route and see why not nanocellulose and nano-based or nano-bio-based materials as well. So the first thing that we tried to do this was like really early over there with the material that Panu produced at VTT and let me bring with me when I moved to Auburn. So we used these nanocellulose suspensions and tried to understand whether there was an impact or not with the presence of lignin on it. And we used these nanocellulose suspensions to inoculate fipronil, which is an insecticide, into southern yellow pine seedlings. And fipronil is an insecticide that is used to prevent pine beetles attack. So pine beetles cause billions of dollars of losses in the United States. And this is a very nasty insecticide that is applied and doesn't not only affect the health of the workers, but it's also very expensive for the silviculture practices. So what we did was we inoculate these seedlings in the nursery, and then we monitor the amount of fipronil over time, and we monitor the amount of fipronil in the pine needles over time up to 18 months, which is supposedly the life of the insecticide in the plant. And to our surprise, the lignin-containing nanocellulose in the 1/4 of a recommended dose of fipronil, it was still detectable in the plant. So this sparked a lot of attention, and we decided to explore more, not only with the adjuvants, but also with those prills of regenerated cellulose, and see if we could use those as a carrier both for fertilizers as well as pesticides. So back to Diego's work. So we Duber is currently working on this project. So what we did was load these beads with, in this case, like what you see here at the active ingredient. This is a NPK fertilizer, just like regular commercial NPK. And by loading these materials, we were able to load them up to like 95% of their weight with the material, because cellulose is very hydrophilic. And then we would load them, we would dry them and use them as a potential slow release of agrochemicals as well. So the first proof of concept we did with this material, which was like simply cellulose and loaded in this case with imidacloprid. And we went back to the nursery with these wonderful ladies here from the Southern Forest Nursery Management Co-op at Auburn that serve over 90% of the southern yellow pine producers in the states of Alabama. So what we did, we used again imidacloprid as another insecticide, loaded cellulose prills, and we put them in the seedlings, and then again we monitor the remaining imidacloprid on the pine seedlings over time. And to our relief, after 3 months of using these materials, the imidacloprid that was encapsulated in cellulose was still detectable at a much higher concentration, meaning that the protection of the crop was extended by the presence of cellulose. However, of course, again, in the case of fertilizers, cellulose being a very hydrophilic matrix releases the material very quickly. As you can see here, the NPK release over time was done in a matter of minutes. So we started exploring, and this is one of the examples that we've been working on with our colleagues at Johns Hopkins and the Connecticut Agriculture Experiment Station down in the States, where we created a hydrophobic shell using vapor gas, the esterification of these prills, and try to tune this control the release rate of these materials. So this is work in progress. The good news is that these materials, after esterification, they're still biodegradable, and we can still use them and create more sustainable carriers in lieu of the acrylate materials that they are currently use. So there are like several ways that we can use cellulose-based materials into agriculture. We can think I show you some soil system by drenching these adjuvants of cellulose nanofibers. We can use also those suspensions as a foliar delivery by spraying. There are like common practices that we learn over the time of this project with the right partnerships. But we, like long story short, is that without any treatment and the way that the current practices in agriculture are, only 10 to 20% of those agrochemicals are taken advantage by the plant. So this paragraph here is something that our colleague in horticulture helped us calculate based on some of our data. And again, if we are not really selling our point of sustainable materials for agrochemical, we definitely are going to sell, or we have the data backing up that this is also an opportunity to save the farmers a lot of money. So over COVID and the after COVID math has created a lot of challenges for the farmers in the United States with the skyrocketing prices of pesticides and agrochemicals. So our technology could help this industry by reducing the costs of production, which will translate also not only in improved crop yields, environmental effect and environmental protection, but also in strengthening the economy of the agriculture and the food sector in the States. So another project that I picked today to share with you is an initiative that we started working also a few years ago together with our partners at the CDC, where we started looking into cellulose-based fibers as carriers for pesticides such as permethrin and other mosquito control insecticides. So the malaria control in Africa costs millions and millions of dollars every year, where the United States through the CDC ships lots and lots of mosquito nets that they are polypropylene based, and they end up as a source of a large contamination because their durability is very low, and also they create several cultural issues that people do not really want to sleep under a white cloth in Africa. So there is a very critical issue with waste, but also with malaria control. Most of the population that dies of malaria are children like younger than 5 years old, and this is a real world crisis. So we started working with Michael Hummel and our colleagues at VTT as well, Hannes and Alistair. I didn't really find any decent pictures of you on the internet, so you need to get your game going. We work together. This is Sarah Sodi, who is our CDC ally. Back in the times, she was in the first Trump administration. She was President Trump malaria director for all these initiatives, and we had the fortune to go and present this work to the RBM partnership to end malaria in Rwanda last year, and yet there is a very much interest in sustainable materials, yet the price and all the issues with the production costs is still an issue. However, we believe that the technologies with ionic liquid dissolution, it might be an opportunity for us to create these like long-lasting insecticide fibers. So back in the very early beginning from FinnCERES, Michael And Hannes got some funding to bring Sydney, who is a PhD student in my group, and she came right after COVID to do some spinning of these fibers. So what we did was like to load cellulose fibers doped with permethrin and PBO, which is a synergistic, because now mosquitoes are resistant to everything, so especially permethrin. So PBO is a synergistic. And she was able to spin these insecticidal fibers, and with the help of Alistair, we determined that they after the dissolution and regeneration process, they still keep about 70% of the permethrin in the fiber and 30% of the PBO, which might seem low to you, but it's very similar to those levels of retention of this insecticide in polypropylene long-lasting insecticidal fibers. So we're very excited about this work. Sydney came back last summer again, and we continue this work, and also with FinnCERES funding. So we appreciate that support as well. So another area of work that I wanted to share with you, we did these polysaccharide assemblies that we've been developing. This is the work also that Diego did with some support from NSF. That career work was to modify both cellulose fibers and chitosan using cyclodextrin. In particular, this work started by try to capture microcystins, which is this toxin that is created by these algal blooms, that they are very common by red or green algae, whether it's like fresh or salty water. And it's a real issue. So we started looking into cyclodextrin modification of polysaccharides and trying to use that hydrophobic cap of the cyclodextrin to capture that microcystin, and then use those materials to assemble them by adsorption. In the case of chitosan modified, cyclodextrin modified chitosan on cellulose fibers, and then whether use that as a coating for prills, for the cellulose bits that I mentioned earlier, or the lignify good porous structures of wood. So in both cases, we had positive results where we could improve the absorption of these the microcystins from spike water, and we this was mainly the seminal work. We did this also with the collaboration with Wim Tielemans in KU Leuven as well. So we started playing around with all kinds of modifications of these bits. We were able to attach a propagated chitosan on the cellulose bits to create a clickable material that it could be used as either detection or absorption of emerging contaminants. We also use chitosan in the solution bath for the regeneration, so we could add different type of functionalities. We also use cellulose or hemicelluloses from other sources like tarragon residues and all kind of low-cost materials, and try to assess the opportunity to improve the absorption capability of these bits. And also back to the issues that they are like common in the southeast, in Alabama, and in the whole southeast. There is this invasive species of wild boar that destroys the agriculture and causes many $1 million a year in the agriculture sector, because they eat everything and all the rooted systems of crops. And they also, while they eat, they also defecate, and they contaminate water with E. coli. So we modify this cellulose bit and decorate them with silver particles, and we create this filter that ideally will be a multifunctional system that will not only remove bacteria, but some other of the contaminants that we've been working with. So to date, we have been able to address different contaminants. We created these polysaccharide materials or assemblies to uptake or regenerate water from dyes, toxin, pesticides, bacteria, and as well as metal ions. And one thing I wanted to mention around this journey in the 9 years I've been in Alabama, so very common also to other states in South Carolina. There is a lot of potential for this forest industry to use the forest industry supporting education of particularly underrepresented minorities as well. So we have a ranked in the in the states, according to the Sustainable Development Goals, is the 45th out of 50 states in terms of environmental education. So we are really doing very poorly in environmental education in the Southeast as well. So we can certainly think about I'm sorry about that, I don't know what happened with this, but the Sustainable Development 4, which is quality education, we could think about that development goal, and again, food for thoughts for everybody is like, we can consider this goal as the one that rules them all, because if we can educate the population, the community, and the different stakeholders, we can make a leap advance in improving the quality of life of our the citizens as well. So Carly Cummins did a lot of work in this area, where we studied assessing the gap on sustainable environment and sustainable and environmental education in the state of Alabama, and according to the Alabama STEM Council, in 2022. 37% of the Alabamians were educated in environmental science, and indeed we try to understand this by collecting data. And what you see here in white is what they call, today they call it the black belt, where all the marginalized back slaves, where all the civil rights movement started in Alabama. And we've been working trying to implement different mechanisms, formal and non-formal, of education, trying to involve the community and try to make a difference in that. And I know my time is up, but I will say one more thing in the terms of internationalization. Also, we are working on this initiative, also with Tekla and Orlando and many other here in the room and not in the room, in a program that is aiming to bring a network of networks together to advance commercialization and remove commercialization barriers for bio-based products, bringing AI and machine learning as well. This program doesn't exist anymore as of last week, but we are going to continue working on that and invite you all also to reach out and see if you're interested in to work with us. And with that, I would like to thank all my students present and past, and there is Autumn here, one of the first students in my group, and I'm very happy to see you here, and all my collaborators and the funding agencies. And thank you, ladies, for the invitation, and thank you all for bearing with me today.
Honored guests and innovators, both here and online. Welcome to this accelerator section of the World Bioeconomy Forum entitled The Bio-Based Future. O futuro de base biológica, em português. My name is Luana Dessbesell. I'm an assistant professor in Sustainable Bioproducts Innovations at Aalto University. And it's an honor, an excitement, and a little bit of nervousness to open the session that beckons towards a new horizon, a world where the foundation of our economy is not only circular, but in harmony with nature itself. This year's forum is organized in São Paulo, and it focuses on exploring tropical solutions for sustainable growth with the power of regenerative economy and strategies of a bioeconomy. It emphasizes the indispensable role of the production sector in driving towards a circular economy. And this accelerator session is led by FinnCERES, the Competence Center formed by Aalto University and VTT, Technical Research Center of Finland, is funded by the flagship program of the Research Council of Finland. And today we have the pleasure of featuring Dr. Hanne Wikberg from Chempolis, discussing the technologies transforming biomass waste into valuable. And we also welcome Dr. Caio from Unicampi, presenting on materializing circular plastics from food waste. Our session will also welcome the pitching of FinnCERES proof of concept projects. Let's pause for a moment, because we are at a crossroads. We have had amazing talks today, and a lot of what we are going to talk about now is how we go from linear models that we know are built on extraction, we know lead to a lot of consumption, disposal, and we know it's no longer an option. So We know our resources are finite, our ecosystems are fragile, we are already facing the impacts of climate change. So we must embrace this transformative approach, not only to mitigate these things we already know, but to turn them into opportunities for regenerative, sustainable growth. I want you to imagine that the materials we are developing would be made entirely from renewable resources. They would last longer, they would be biodegradable. Picture cities beautifully run by green infrastructure that are supported by bio-based solutions that clean our air and water. Imagine, dream, we are allowed to do that. Envision transparent supply chains that optimize resource efficient. That is the bio-based future we strive to create. Consider the incredible progress we have already made, and we also have discussed it before. The technological innovations are transforming waste into valuable materials and products. The business around the world recognize that the bio-based approach is not just an ethical option. It's actually an opportunity for competitive advantage. The forest and allied sectors are crucial in this transformation, especially when enhancing circularity, decarbonizing, and safeguarding biodiversity. The sustainable transition within the forest industry will and should catalyze the transformation of other sectors. However, transitioning to a bio-based future is not without challenges. We must navigate technological hurdles, overcome market barriers, foster interdisciplinary collaboration, policy frameworks need to evolve, and public awareness need to be in place for drive the demand of future bio-based products. Today, we are not just sharing ideas, but building global collaboration networks. We are not just envisioning a future, but drawing a path towards it. Each of us plays a role, researchers, entrepreneurs, industry, policymakers, consumers. So let us approach this session with the curiosity of pioneers, with the rigor of scientists, with the passion of advocates. Our bio-based future is not a distant dream, it is within our reach. And our collective responsibility is to turn that into reality. Let's harness the power of nature, rebuild our economy with the principles of sustainability, resiliency, and circularity. So thank you so much for your commitment. And let's accelerate the journey towards a bio-based future together. Our planet, our societies, and the next generations yet to come will thank us. So welcome to the bio-based future, and let's begin.
Okay, hi everybody. I'm Hanne Wikberg, and I'm the Product and Business Development Director at Chempolis. Some of you may know that there has been some changes in Chempolis quite recently. So as a consequence of company merger, my former employer Fortum Bio2X team merged with Chempolis late last year, and this is now the place of the Bio2X team. So we all are working under the same roof at Chempolis, and we also have a new owner, AM Green. So today I will tell you about Chempolis and what we do with the title Transforming Biomass into Value with Organosolv Processing. Happy to be here. Thanks for inviting me. Yeah. Okay, if I start shortly by telling you about Chempolis, what we do and what we offer. So Chempolis is a Finnish company focusing on developing and commercializing biorefining technology based on organosolv process called Formico to turn non-food biomass into high-value bioproducts with high resource efficiency. Chempolis technologies enables, for example, the production of bioethanol, cellulosic pulp, cellulosic sugars, biochemicals, as well as high-purity lignin from many kinds of feedstocks. Chempolis' business model is to license the technology to our biorefinery customers. We also offer conceptual process and plant engineering to our customers, and we help our customers in the product development as well as sales of the biorefinery products. And we do have a pilot plant in Oulu, Finland, where we can produce our bioproducts from tens to hundreds of kilos. And we also offer full-scale testing services and scale-up services for all clients under the concept Open. In addition to Finland, Chempolis has operations in India. If I start by telling you shortly about our few public projects. So our first biorefinery, ABEPL, will start its operations still this year in India, Assam. ABEPL will use bamboo as a feedstock, and it will be producing roughly 50 kilotons of bioethanol, 19 kilotons of furfural, 11 kilotons of acetic acid, and their lignin will not be separated in this first-of-a-kind biorefinery, but instead used as so-called biocoal to produce steam and energy for the plant purposes. But anyway, this will be a proof of concept of Chempolis technology in industrial scale, so a very big milestone for our company, I must say. And here you can actually see a pretty recent picture from Assam, and as you can see, it almost starts to look like a real plant. We also have other public projects. So, for example, Nordfuel selected Chempolis to be their technology provider for the biorefinery to be located in Haapavesi, Finland. In Nordfuel's biorefinery, they will be producing roughly 70 kilotons of bioethanol, 90 kilotons of lignin, and in addition, furfural, acetic acid, biogas, and CO2. And this biorefinery will be using roughly 300 kilotons of sawdust and logging residues as feedstock. We also have other project initiatives in the pipeline covering many continents and also very exotic raw materials. So I will tell you more about those exotic raw materials now. So what is really unique with Formico technologies is that we can use almost any biomass and produce high-quality bioproducts from the biomass with high resource efficiency. I have heard that in the past there has only been something like few biomasses that have not really been working well in our process, while Chempolis has been testing tens and tens of different kind of biomasses over the years. So in this picture and in the table, you can see a selection of feedstocks that we have been successfully using in our laboratory and pilot to produce bioproducts. And as you can see here, there are many high-volume agricultural residues like straws and also like energy crops like fast-growing grasses, bamboo, but also wood. So different kind of wood species and also pretty exotic ones, at least in the Nordics. So this is, you can get an understanding on what kind of biomasses we can really use with our technology. So the Chempolis fractionation process fractionates almost any biomass into its main components, our bioproducts, cellulose, hemicelluloses, and lignin, with the yield that corresponds to the original composition of the feedstock as well as the processing conditions. So, and these bioproducts can be used in a wide variety of different kind of applications. So what we have, for example, now been studying with cellulose is that cellulose conversion to bioethanol and, for example, further to SAF, sustainable aviation fuel, or cellulose can also be converted to sustainable textile fibers. Then with hemicellulose, we are mainly concentrated currently on furfural and further conversion to furfural alcohol. Our lignin has successfully been tested in many kinds of applications, including resins, adhesives, foams, thermoplastics, and cosmetics. and in many kind of functional additives. Today I will not concentrate on lignin, even though many of you maybe know that lignin is my favorite topic, but let's drop it for today. And how we do our product development today is that we do a lot of collaboration with our customers and partners, being, for example, research organizations, universities, big companies, startups, and technology providers, for example. Yes, and to give you an understanding on our technology and how it is really working, I'm sharing you now one concept which we are currently developing a lot. So this is a concept that is focusing on maximizing the bioethanol production. So here, in the first phase, our biosolvent, which is a mixture of formic and acetic acid, selectively dissolved the biomass except the cellulose. So cellulose in the solid form is then separated and further purified by washing with water. And pure cellulose is easily then hydrolyzed to glucose with enzymes. And then cellulosic sugars are fermented to ethanol, which is further purified. The spent liquor containing then dissolved lignin and hemicelluloses are evaporated and vaporized, and streams rich in biosolvent are distilled into water, and here also the acetic acid and furfural that are formed in the process are separated. The lignin in spent liquor is precipitated using water and further separated using conventional liquid-solid separations, and then we purified it by washing. And the hemicellulose-rich stream is then evaporated and concentrated and sent to fermentation. So this is one example of the process concepts that we are now working with our customers. And as you can see, and as I mentioned, we can tailor-make the concept regarding to the needs of our customers, which further increases the flexibility of the technology in addition of being very suitable for various biomasses. I will now share you some results from the experimental work that we have been doing and for the biomasses which we are now currently working on a lot. So, but as we all know, we must remember that biomass is a heterogeneous raw material and its composition depends a lot on where it is grown, when it is grown, also the specific species it represents. So the results I'm showing you may not necessarily represent like the typical average value of similar biomasses, but I'm showing you this to get a better understanding how our technology is working. So right now we are working a lot, for example, with wheat straw, rice straw, bagasse and bamboo. And our aim is to produce as high quality bioproducts from these biomasses as possible, meeting the requirements of the final applications. So if we start by looking at the analytical results of these biomasses and their compositions, as we all know, there are big variations in the compositions between different kinds of biomasses, and I would say that these results are well aligned with the literature. And what we can really see here is that the cellulose amount is higher in bamboo and bagasse than in wheat straw. And then with lignin, the content of lignin is the lowest for rice straw. For hemicellulose, the pentosanes really tells about the hemicellulose contents. That's like pretty much the same. And as you know, straws, especially rice straw, contains high amount of silica, which you can also see here, and that contributes to the higher amount of ash. So if these different compounds in the feedstocks end up in different phases and different bioproducts during the processing. Luckily, we have ways to steer the transfer of these unwanted components like silica in the process, and this gives us the possibility to work with such difficult biomasses containing, for example, high amounts of silica. Now, if you look at the product yields, we can see that we can recover very much almost all cellulose as our valuable cellulose fraction. High purity cellulose is easily enzymatically hydrolyzed into glucose with typical yield of over 98%. With lignin, we can also see that the recovery rate with our recovery method is really high, over 95%. And then with furfural, the yield varies depending on the concept, if the aim is to maximize the furfural production or use the hemicellulose for additional bioethanol production. And this is why the range is so big, from 3 to 9. And typically the amount of acetic acid is up to 3%. So these values represents pretty typical example of the bioproduct, but what I want to highlight here is that with cellulose alternatively, we can go to sustainable textiles, so we bleach the cellulose fraction to meet the requirements of the dissolving pulp. And in fact, we have proven already that our straw-based dissolving pulp is compatible with well-established fiber processing technologies like viscose and lyocell, but also with emerging new fiber technologies like Spinnova and Infinited Fiber Company. And for example, world's first straw-based clothing and also the whole collection was done a few years ago by an award-winning Finnish designer, Rolf Ekrut. And then with lignin, we can go to many applications like which we have piloted successfully, for example, the resins in plywood and for example, rubber additive. So I would think that my message also is that when going with biomass to industrial scale, we must make sure that we run enough pre-commercial tests to make sure that then the biomass is really working in industrial scale. For example, there is over 100 different species of bamboo. We have now been testing something like 10, so I'm sure that in our path we will still find many new discoveries. But anyway, I hope this gives you a good understanding of the basics of our technology, and thank you for your attention.
Thank you very much for having me. It's a pleasure. It's funny that the event is being broadcast to São Paulo, where I live, but I came all the way here to share with you some of our recent progress, not that recent, but from a decade of research on converting waste biomass into materials. So it's also good to be back in Finland. So I first came in 2019 as a postdoc in Orlando's group, and then after 5 to 6 years, first thing I did was taking a picture of my favorite spot in campus. So it's really great to be back and see many familiar faces. Also a coincidence that the forum happened 2 years ago here in Helsinki, and now in my home country in São Paulo, in Brazil, more specifically in the state of São Paulo. And the focus is on circular economy, right? And the title of this session is Alternative Biomass to Produce Materials. Of course, all of us share common interest in accelerating the transition towards a circular economy, right? So getting rid of the take-make-waste strategy and create a cradle-to-cradle approach, right? And we have to choose a background, a niche where we want to make a progress, right? And when we see how materials affect the transition in the society, we see that there are many stages in which specific classes of materials are dominating, right? We had the age of stone, and then we have metals taking over. And after 1920, right, after Staudinger proposed the macromolecular theory, we can see a lot of increase in plastics. And people say that we are facing now the age of polymers, right? People dare to say that. This is good because we are a fan of plastics, but it also comes with a lot of stereotypes and bad consequences for health and for environment, right? This is triggering, for instance, a global treaty triggered by the United Nations against plastic pollution, right? See, against plastic pollution, not against plastics. But still, people trying to get rid of plastic pollution and trying to find more sustainable alternatives to boost this class of materials that is really important for today's society. In Brazil, I manage this National Institute of Science and Technology called INCT Circularity, and there are 60 plus of us researchers from all over the country, research institutes, universities, companies, doing research in the different angles of circularity in the context of polymeric materials, polymer-based materials, right? I'm here in the Southeast, and we have different institutions working on 5 main technical work packages. The first one of them is the topic of today's talk, that is getting rid of virgin natural resources, regardless if it's fossil or natural or bio-based or rapidly renewable, trying to reduce the input of virgin raw materials in the materials processing chain. The second one is, of course, increasing the quality and extending the shelf life of materials so they last long, which is also aligned with circularity. The third one is with the grave, right? Quoted with the grave. After consumption, what we do with the materials? Do we recycle chemically, mechanically, enzymatically, thermically, physically, right? Biologically, biodegrade, and so on. The fourth one is kind of transversal, so it's quality and safety. So we are worried with the additives, for instance, with the intentionally added substances, and with the NIAs, with the non-intentionally added substances that are generated through polymer recycling cycles and utilization as well. And the fifth one, of course, is quantitative metrics and indicators to quantify how we are doing in terms of circularity. So, of course, as the topic is for alternative feedstocks and technologies, this one is a no-brainer. I'm fortunate to have a lot of good talks introducing the topic, right? But this is a no-brainer, fossil versus biogenic carbon. But if we think of biomass, virgin biomass is also virgin material. So the angle that I want to put forward here is to use residual biomass, things that are not virgin, but upcycled into materials. So we reduce the resource input in the environment, and we maximize waste prevention. I should have quoted my thought. Actually, it's quoted because this is a Nature paper from like a decade ago saying don't waste food, seafood waste actually, right? Because besides feeding the population, there is a lot of interesting particles, molecules, substances in the side streams of food production in general, right? And I know several groups in this room that work exploiting, crab, shrimp, different stuff to recover chitin, these polysaccharides, or inorganic materials, carbonate, and so on. In Brazil specifically, Brazil is a large country with an agro-based economy, right? And we basically help feeding the population, the world population, because we produce a lot of specifically soybean, cattle, what else? Sugarcane, oranges, maize, like corn. So different cultures are spread all over the country, cassava, right? And we are big producers, meaning that we generate a lot of waste. And this is an opportunity. I at least see it as an opportunity. And there's always the debate when competing for biomass for food and for materials production, right? So we are a tiny fraction, right? Using waste for materials production. I mean, using biomass for materials production. But still, there can be this discussion. And then we put forward the angle of using only the residual biomass. A few years ago in 2021, we kind of put together with Orlando, Bruno, and guys in this audience, like design rules to convert whatever we can recover in terms of monomers, macromolecules themselves, colloidal particles. We can process them into converting into polymer-based materials that using specifically and only food waste. And bearing applications, like we call them advanced, but not as advanced as like sensors and actuators, but also simple packaging as the topic of today's talk. We started actually in the group working with that like 15 years ago. This was the very first example. We had a project with a company, with a fishery company in Alaska, and they were doing the fillets of the fish they caught, right? But a lot of this skin, of the scale, they were thrown away back into the ocean. So we were able to recover collagen, denature into gelatin, cross-link with UV radiation to produce flexible, transparent films that we used for packaging applications. This was a proof of concept that a few years later was extended to overripe fruit. So with another company, this fruit supply company in Brazil, they had a lot of overripe fruit, papaya, peach, guava, strawberry, that they were not bought because they were not attractive to the consumer, but still it has vitamins, pigments, flavor, and also film-forming polysaccharides, right? So we managed to produce these small, like A4 page films, flexible films, that later were scaled up to meters, like 10 meters of film per hour. So this is a continuous lamination machine that we used for scaling up the production. There is, of course, a doctor blade that you can control the wet thickness, and then there is an infrared pre-drying stage, 2 oven drying stages that are independent, so you can do co-lamination, multi-layers of films as well, and then you wind your film based on food waste at the end. We worked a lot with a big tomato processing company in Brazil as well. So they were generating tons and tons per day of seed, skin, pomace, right? And it's of course reaching biopolyester called cutin. Someone mentioned suberin earlier today. This is a cousin of suberin called cutin, right? That is responsible for hydrophobizing the fruit cuticle in tomato, in olives, in apple, in coffee beans, right? So we were recovering this molecule specifically and decreasing the water vapor permeability and increasing the water resistance of pectin of highly hydrophilic films as well, right? There was a little bit of colloidal science to prevent phase separation and to get even film, and at the end we managed to do one of those films. And finally, for what we call the vegetable biorefinery, we were working with a company of a minimally processed carrot, and we were using only whatever was left, right, the side streams of the production, pieces and even cuts and so on. And we were converting them into flexible films, which the properties we could adjust using like a binding agent, cellulose, soluble hydroxypropyl methylcellulose or anything similar, also reinforced to control the properties. This you can buy online in the States, so you can buy in Amazon, in Trader Joe's. This was developed at USDA, which I shared an affiliation earlier. You can buy in different flavors. It's for edible films, but this is not from a carrot waste. This is from carrot puree, right? And the angle that we put forward now is to use only the waste and for application as packaging, for instance. But we also, besides working with the biopolymers themselves, we also recover as additives or property modifiers some colloidal particles that we use to assemble materials. So Brazil is a major producer of sugarcane, maybe one of the largest in the world. This means that a lot of straws and bagasse are generated, and there was a student working in a plant, in a real plant. She was recovering the straw and the bagasse, and we were converting this into cellulose nanofibrils with residual lignin or not for colloidal applications, but also for producing flexible films. I didn't want to skip this example because it was led by Bruno, who is in the audience here in Aalto. And they were, together with Andrea, they were using waste wood to recover tannins and to produce these nice, beautiful foams that are flame retardant and also thermal insulating. And also to produce these films that were like UV shielding, right? So it's transparent in the visible range, so you can see through what is packaged inside. But the UV light is kind of blocked, so that is more detrimental to food shelf life from the food shelf life perspective. There is also this I wanted to mention from Orlando's group, led by Marco and Bruno as well, that they were recovering chitin and cellulose nanofibrils from insect waste. So these emerging proteins, they left behind a lot of exuva and exoskeleton. So they were recovering these colloids also to produce these films that you can see here. And lately, we've been trying to avoid fractionation to process things as a bulk, altogether, because we understand that every step adds cost, adds footprint. So we are trying to avoid fractionation and as much as we can pretreatments. So in this work by Leticia and by Lais, we are using orange that we produce a lot in the state of São Paulo, either with the fractions or all together. So the bagasse, the pomace, and the peel. We do mild pretreatment like hydrothermal and mild acidic pretreatment to get these beautiful flexible films and also foams that are being used for thermal insulation. In this case as well with Rodrigo, we have been working only with the banana peel. So banana goes to the market, right? So there is nothing more noble than feeding the population. So we work only with whatever is left. And also we produce these flexible films that you can see here. This is a Brazilian company. It's the translation says, I've already been cassava. So it's basically cassava starch, right? They work with these rigid containers, semi-rigid containers. They have a big portfolio. And we've been trying lately, this is still ongoing, trying to do something similar using coffee bean waste and also waste from the winery industries from grape pomace. So using, thermal forming and hot pressing to produce these guys as well using expanded, right? It's analogs of EPS, of styrofoam, but only using food waste. And just to finish, we work with biodegradable materials, but I guess it can get more circular if we, instead of biodegrading in converting the solid state carbon into CO2, to say the least, maybe methane, depending on the conditions, we've been putting forward this approach, and this is just recent, we just published this year, of chemical recycling of biodegradable materials. So regardless if they are biodegradable, we've been using like zeolites and ionic liquids to catalyze the depolymerization. In this case, it was a beta-glucan film, so it's a polysaccharide. We've been doing this now with other polysaccharides. So we have a film that is from a renewable source, of course. We process them into this packaging material. And instead of sending to the grave for biological recycling, we go the green route. We selectively depolymerize into the monomers or oligomers. It depends, right? And this can be used again for repolymerization or open loop recycling, such as the last example that was missing here, right? To get monomers from food waste. And in this case, I'm showing the case of glucose that we recovered from glucan, right? So glucose is, of course, a platform chemical that can be used to produce several materials, including thermoplastics that are commodity or specialty plastics like polyesters, polyamines, polyurethanes, and even polyolefins. That is what Braskem does in Brazil. So they produce ethanol from fermenting glucose, they dehydrate into ethylene and polymerize into green, what they call green polyethylene, right? There are, of course, other monomers that we can recover from food waste and transform into different classes of plastics. What I wanted to say is that when individuals, when companies, when they throw away their resources, even if they consider them side streams, I don't want to say residues, right? Because we know that it can be byproducts that can feed different cycles within the circular economy framework. When they do that, they actually throw away not only the resources, but also the opportunities to make profit and to get a lower footprint. Of course, there are drawbacks, many, right, as all of us know. In terms of seasonality, variability, cost, of course, scalability, supply chain complexity, right? So we compare the petroleum supply chain is well established, regulation as well is well accepted and well established. But of course, if we consider the last row, we understand that in the future, this, for instance, this global treaty against plastic pollution will bring this role to increasing importance, and maybe someday this will take over and we can feed like the plastic industry with more biomass and specifically more residual biomass if possible. Of course, this is connected to several of the SDGs. This has been mentioned several times before today, right? But I wanted to highlight number 17 that is often neglected, right? 17 is the partnerships that are established to reaching the 16 former goals, right? And I guess this is all, what FinnCERES is all about. We are here to establish connections and to create partnerships, merging competencies towards all of those 16 goals that are here. So I wanted to thank you for your attention, for having me, and happy to take questions.
And next, we will hear brief highlights from the FinnCERES Proof of Concept project, showcasing cutting-edge research on applications ranging from carbon capture to electrochemical sensing to sustainable batteries and cellulose-based textiles. First up is AC Film.
Hello to everyone, and I will start with something simple, like a glass of water. You probably have it in front of you, me as well, and we're just drinking without giving it too much thought. But let's just quickly go through several aspects that actually do impact our drinking water. So the first one would be microplastic. This is not something new. This has been quite a hot topic for many years. But when it comes to microplastics in the wastewater treatment, we have some of the technologies, for example, membranes that are made from fossil fuels. So upon disposal, they can be a source of microplastics themselves, right? So next aspect would be just, we have different kind of feeds, we have different kind of pollutants, dyes or pollutants, or what else? Well, to name a few. And the third one aspect would be a rapid industrialization, urbanization, and other things. So we have these three aspects, and you would think, like, what can we do differently? What can we do to take these things into account? And since we are at the bio-based futures, you probably would say, oh, we have, well, maybe cellulose. And you would be right. Yes, cellulose, it works. But the problem with cellulose, it loves water. It's not that mechanically stable, especially when we talk about wastewater treatment. So again, what can we do? And that's where our projects come in hand. So at the AC Films, we approach to do is the thin film composite structure. So kind of like a sandwich approach. So how do we achieve that? So we have our supporting structure that can be paper, that can be textile, also cellulose as well. Then we have our microfibrillated cellulose, basically like a middle layer. And then to achieve the thin film on the top of our sandwich, we use our solvent, which can be ionic liquid, for example. So that's what we are working with. We just started, so stay tuned for updates, and thank you for your attention.
Thank you so much. Thank you so much. And our next presenter comes from Bioptex, Hannes Orelma.
So thank you very much. So our project is called Bioptex. So and we had now developed like several years now in under FinnCERES this topic. So and now we are going to closer of more industrial applications, and we have found like this immunity diagnostic sensing. It could be actually rather good application for these cellulose-based optical fibers. So we are aiming to label-free detection with small sample size. That is our sales argument. So and then you know there is many challenges what doctors have. Then to like analyzing diseases, they need expensive instrument. Sometimes they are very difficult to use. So we want to develop something very fast. And here is the system what we are developing. So there is the combining optical fibers and then liquid flow. So right up there is visible the portable system what we have now. So, and then it's combined to flow cell technology, what we are developing here. So, and here is the team. So I and Olli, we are leading this. Ayus is our doctoral student. And then we have optics team. And then business expert. Yes, thank you.
Thank you very much, Hannes. Next up is Mikko Mäkelä from Selnas.
Thank you very much. Just one slide. So automated sorting systems based on near-infrared sensors are currently breaking ground in the textile field. These systems can identify common fiber types for sorting applications, but their ability to estimate detailed polymer properties for recycling are currently not known. Textile sorting and recycling are timely topics, as the average European now generates 15 kilos of textile waste every year, and the European Union now mandates that member states organize separate collection of textile waste since January 25. Now, we've recently developed a patented technology that can estimate the polymer properties of cellulose for recycling. These properties govern the viscoelastic behavior of dissolved fibers, which must be monitored and controlled during recycling. In this proof of concept project, we will combine this technology with computational simulations and X-ray scattering to study the degradation of fibers in the lab. In the project, we have three main objectives. First, we want to understand the mechanisms of cellulose degradation in textile fibers. Second, we want to simulate in silico near-infrared spectra to understand what we are actually measuring with this technology. And third, we want to achieve TRL4 by lab-scale validation to achieve high prediction accuracy for these properties. This project has considerable economic and industrial potential. In the short term, we estimate that it can save over 10,000 euros an hour by avoiding process disturbances in a large-scale recycling facility. In the long term, we estimate that it's not only limited to textiles, but could be applied to the broader field of cellulose modification through, for example, regenerated cellulose films or even pulp suspensions, which offers an already existing multi-billion euro global market. Thank you very much.
Thank you, Mikko. Next up is CellSense and Vasuki.
Thank you, Nina. Good afternoon, everyone. When I introduced my research on electrochemical, sorry, wrong directions. When I introduced my research on electrochemical sensors, I often refer to glucose sensor as an easily relatable example. However, electrochemical sensing itself is a simple yet potent technology that can, in principle, detect an infinite array of substances, everything from pathogens to PFAS. So then why is it that while glucose sensors have evolved exponentially over the past 6 decades, there is still an acute lack of similar off-the-shelf sensors for other substances? Wouldn't it be nice to have an easy sensor that can monitor, for example, the vitamin D in our body, given how elusive the Scandinavian sun is? Unfortunately, while a healthy human has about 0.8 milligrams of glucose per ml of blood, there is less than 40 nanograms of vitamin D. This means for an electrochemical sensor to be able to measure vitamin D from our blood, it needs to have over 20,000 times higher sensitivity than any glucose sensor. And sensitivity is only one of the challenges in sensor design. To make the jump from research to reality, an electrochemical sensor for a particular substance must fulfill several critical parameters, including selectivity, stability, and scalability. Sensor design is thus an infinitely iterative process requiring the unique tailoring of electrode material properties for every target substance. There is no one-size-fits-all solution. However, our research offers a rather elegant solution to this complex problem. We found that the humble nanocellulose, when mixed together with electrochemically active carbon materials, brings several key functionalities to the resulting hybrid electrode material. For instance, the hygroscopicity of nanocellulose enables enhanced analyte transport in the electrode, thereby increasing the sensitivity by several orders. Further, by controlling the surface functionalization of nanocellulose, we are able to tune the ionic interactions within the electrode, thereby increasing selectivity to specific molecules. In this proof of concept cell sense project, we also aim to tackle the sustainability of such sensing platforms by replacing conventional fossil-based materials and critical raw materials with bio-based alternatives. The overall objective of cell sense is therefore to develop and demonstrate an industrially scalable, bio-based electrochemical sensing platform that is not just sustainable, but also offers superior performance compared to existing market alternatives. Thank you.
Thank you so much, Vasuki. Next up is Tuuli Virkkala from CoFoam.
Thank you, Nina. We are all aware of the huge contribution of carbon dioxide emissions to climate change. According to the International Energy Agency, there's currently a yearly gap of nearly 800 million tons of carbon dioxide for reaching the 2030 net zero emission target. At the same time, each year, up to 1,000 million tons of carbon dioxide is also needed for replacing fossil-based carbon resources. Here in Finland, the forest industry generates roughly 20 million tons of carbon dioxide annually. And what if these emissions could be tackled by collecting the carbon dioxide already at the site of its generation, which could then be converted into a bio-based carbon feedstock? Drawing from previous fundamental research on the influence of fiber water uptake on gas adsorption, the CoFoam project aims to untap the potential of the inherent properties of natural materials to create moisture-responsive solid foam sorbents for water-assisted carbon dioxide capture. Nanocellulose-based structures have been demonstrated as promising carbon dioxide capturing materials, and CoFoam will further expand the raw material base from the forest-based resources to currently underutilized agricultural side streams, such as barley hemicellulose from beer brewing and nanochitin from food waste. We will utilize two strategies to further enhance the material's capturing performance. First, the selectivity for carbon dioxide binding will be increased through amine modification or incorporation of naturally amine-rich compounds. Secondly, the hygroscopicity will be exploited to boost the functionality of the materials and aid carbon dioxide capture. The use of bio-based low-cost materials is an asset of CoFoam, and the technology challenges existing solutions based on liquid amine scrubbing, suffering from energy intensity and low operational stability, and current solid sorbent membranes based on zeolites and metal organic frameworks, which are challenging to upscale and sensitive to water vapor present in exhaust streams. When successful, the CoFoam technology will not only reduce the carbon dioxide emissions from forest industry processes by at least 80%, but also significantly boost the value of cellulose-based products. In other words, the project contributes to generation of novel, bio-based, high-value products, as well as introduces a technology to respond to the demand for carbon and the set targets towards net zero emissions in pulp mills, biorefineries, and beyond. If you're interested to hear more, please follow us along this journey towards carbon neutrality with new added value materials. Thank you for your attention.
Thank you, Tuuli. And next up, we have storage with Andrew Kerr.
Hello, everybody. So to meet goals of net zero carbon emissions, there's been an increase in adoption of battery-powered technologies, such as electric vehicles, and this will only increase in the upcoming years. The leading technology is lithium-ion, which you have, for example, in your mobile phone. but the materials needed for their manufacture are quite problematic, including the lithium itself, but also heavy metals such as cobalt and nickel used in the electrodes. These suffer from safety concerns, they're difficult to recycle, and they're extracted from mining in environmentally damaging ways. So for these critical raw materials, they're also available in quite limited supply from geographically restricted areas, which complicates supply chains. And with the increasing demand for batteries by many projections, we will run into shortages of these materials. So there's a clear need for the development of more sustainable battery technologies with alternative materials, and this will be important for transitioning to using renewable energy sources. So in the storage project, we research organic radical batteries using bio-based substrates, which can be sourced from local supply chains and avoid many of the issues with the critical raw materials used in the lithium systems. We envision a sodium-ion battery design, which has bio-based materials in 3 elements. Firstly, for the anode, a hard carbon will be used, which can be derived from biocarbon feedstocks, such as tannin and lignin. Secondly, as the electrolyte, a cellular-based hydrogel will be used in place of normal solvents in most batteries. And finally, the cathode can be composed of a organic radical functionalized polymer, which means no heavy metals are required in either electrode of the device. Throughout the project, we will refine the synthesis of these materials and establish prototype battery devices in the lab. So altogether, this project could offer a high-performance battery technology with better safety, lower costs, and sustainability. Thank you.
Thank you very much. And last up is Tree to Ink with Anna.
Okay. Hello, my name is Anna, and you must be wondering why is this black slide here behind? Well, if you look around you now, most likely you're wearing something black, or you have something like your laptop, your black backpack around you. And if we go deeper, most likely, what's the favorite color in nowadays, and what color we use in our daily life the most? Black. But have you ever thought about from where this black color comes? It comes from black inks. But how are these black inks produced nowadays? And from which sources is these black inks? So black inks are normally produced by the combination of pigments and binders, which give them this stability and adhesion, making this material a bit less black than expected. But what if we think about just the sources that we're using with them? Pigments are black carbon that can be petroleum-based, and bonds. But look at how much carbon emissions we are generating, and also how much pollution we are generating with this pigments production. And the binders, normally they can be acrylic or even epoxy, and in this way, these binders are not that transparent, and we can decrease the blackness of these materials. And then, about the processes, can you imagine how much money we're using to produce these materials and how much smoke we're generating every day while doing them? What if we could flip the idea of producing these materials? What if we could actually store carbon instead of releasing carbon? That's exactly what this project Tree to Ink is about. Here, we want to create a black ink from wood waste in a way that we can use all this biomass generated from different processes and industry in a way that we can reduce the processing of using low energy processes and carbonization in a way that you can create a deep and really black carbon through chemical processes using less energy and also avoiding these high temperature processes. So In this material, we can create a black ink that can be the result of a material that is fully bio-based, different from the other projects that have been in course, creating something that can be carbon negative and also be utilized in a lot of applications anywhere the black color is needed. Thank you.
Thank you, Nina, for the kind introduction, and I also want to thank the committee for inviting me here today, and especially maybe also Stefania and for arranging everything, and Sana, yes, for arranging everything and taking care of all the practicalities. So actually, I don't like the term waste to fuel, because it is of course not a waste that we're working with. But anyway, let's start with the value chain. So we have the tree, we're all set to this, and there's a lot of streams coming from the tree. The main one is maybe the planks, and you also get some side products. You get shavings that you can make interiors in your kitchen boards, for example. And then you have a big other stream that goes to pulp. And you also have a second side stream coming out from this that is tall oil. But if you look at this and you summarize, you see that the yield is not so high. And the rest goes to incineration in one or other way. So the tops and branches maybe are not incinerated, they're maybe left in the forest. So I want to point out a few things with this slide. First of all, we have a debate in Sweden at least that we should not cut down forest for making paper, for example. We should only make high-value planks from the forestry. But it's very difficult to cut down this tree without getting one portion that goes to the pulp. It's impossible, right? Another thing I want to point out is that the pulp that you produce has a high value, and it's very difficult to substitute this pulp. So, I mean, I worked, for example, in the lignin first community, and we always write in our first introduction that current pulping is inefficient, and because you're not taking care of the lignin. But of course, the pulp that is generated in the Croft process, for example, has a very, very high quality, and it's very, very difficult to substitute this. So if you're developing new pulping technologies, don't try to substitute this. It's very, very difficult. But there is a lot of other streams that you can work with, and our group is working with all of these streams. But today, I will focus on where we started 15 years ago, and that was with Croft lignin. And we started with Croft lignin because we were naive and didn't have knowledge. We thought Croft lignin was just native lignin. And we had built up models, and the models worked in our catalysis, so we thought that, okay, then we can just take some Croft lignin and just apply our technologies on this Croft lignin. But of course it didn't work. But let's look into the process a little bit first. So if you take 1 weight unit of wood in, you get about 50% yield of your high product. And then you get another byproduct that's called black liquor. And the black liquor is not a waste. It's not burnt to waste value. It is used to recover the chemicals. And this is a messy slide, but I also want to highlight that during the pulping, you have sodium hydrosulfide. That is the active chemical.
And during the pulping, this one is also rather selective towards the lignin, so kraft pulp contains a lot of Hemi. During the kraft pulping, the sulfides are converted to sulfoxides and sulfates. And then in the recovery boiler, you have a metathesis going on where the oxygen leaves the sulfur and goes to carbon, and you get carbon dioxide. It's a reduction of the sulfoxides and an oxidation of the carbon. And then you have some ion exchanges, and then you get back your reactive chemical. So something that's important is that this is the bottleneck in if pulp mill start getting some age, we heard yesterday Metsä, they said that the recovery boiler should live for 30 years. You have the option of course, doing as Metsä did, buy a new recovery boiler, but it's very, very expensive. It's more than half of the investment cost of a pulp mill. The other option is, of course, to lower your production. But there is also a third option, and that is to debottleneck the recovery boiler by taking out some of the lignin. And if you do this, you can increase the intake and you can get a marginal tonnage. So you increase the marginal of the pulp mill. So how does this work? Well, the lignin in the black liquor is deprotonated because it's soda. And at some part in the evaporation, between 35 and 50% the dry content, you can take out the part that you want to withdraw. It's normally 10%, but you can go up to 20%. And then you lower the pH. You do this with carbon dioxide. And then the phenolates get protonated and you get phenols and they crash out. And you can filter these. And then you have some sodium left because you also have carboxylates, so you have to lower the pH. You do this with sulfuric acid, and then you get something that's called precipitated and washed lignin. So if you look at the techno-economics of doing this, you get, of course, a revenue for the pulp, but you also have a cost. And you also get the revenue for the lignin, but currently, or now actually there's no mill that does this, but the mills that did it, they incinerate it in the lime kiln. And then you get the heating value for it. Then you have costs, chemical costs, and these are pre-pandemic and pre-war prices. So today it's much higher. And then you have running costs and investment costs, CapEx and OpEx. So if you balance the costs and the revenues before the crisis, there was a small marginal. And taking into account that both the mills that used this precipitation stopped doing it, we can maybe see that this mirrors that the revenue of just burning it is not high enough. So to summarize, this lignin needs a higher value. We also checked the environmental sustainability, and I know that Alessandro Marson here and presented this earlier this spring. And he also showed that just burning the lignin does not, has no environmental benefits. You have to do something with the lignin. And our ambition 15 years ago was to make a biofuel out of this lignin. And we were collaborating with a Swedish refinery, the name is Preem, and they were rather progressive at the time. They were using these tall oils, so it was the first wooden-based product of a refinery, and they wanted to go to lignin. But they had some showstoppers. So first of all, lignin is a solid, and that's not compatible with the refinery. It's not soluble in gas oils. That's also a no-no. And it's polymeric and has a high ash content. So if you want to run it in a refinery, you will run it in a fixed bed, and you will have a co-processing. So you'll have the carrier liquid that is 99% hydrocarbons. There's some sulfur that you want to take out in this catalyst, but it's a hydrocarbon. And then you would co-process it with your feed B. And if it is a solid, then of course it will deposit on the first layer and the reactor will clog. So that's not an option. The other one, the solubility, has another reason. So when you shoot off these oxygens, you generate heat. So it's an exothermic reaction. And if you cannot control this exothermic reaction, you get coke formation on your catalyst bed, and again you get clogging. So in fact, you can have like 5 weight% oxygen in the feed hitting the catalyst bed to have a control over the exotherm. And this you get by diluting your feed with the gas oil. And that is why it's very important that it is soluble in the gas oil, so you can regulate the heat formation. And then the polymer, you can imagine that catalyst comprises a lot of pores, and that these can also get clogged. The hash content, lignin, Croft lignin has maybe 1%. Can you guess what the specification of putting it in here is? Do you think it's 1%, 1 promille, 1 ppm? It's actually 6 ppm. 6 ppm is a very, very low number. And our company has worked 5 years to meet this specification. This is what I would say 80% of our efforts have been lately. So our first approach was to do what people still are doing and publishing, and that is to make a hydrocracking. Let's say you take the lignin, you take a catalyst, you take a solvent, you take a hydrogen donor, and you just beat the crap out of the lignin. And what happens is you get some depolymerization, and you also get some deoxygenation. So we could go down to maybe 2 kilodalton and lower the oxygen content from 30 to 20. But we could still not solubilize this mix in the gas oils. We tried very hard. We could solubilize a part of it, probably the small molecules, but it was not economically feasible. So then we start to get a little bit desperate, and we thought of what can we do to solubilize it. And the economists in our company still didn't like this already, because we're adding stuff, adding costs. So then we thought maybe if we take the tall oil fatty acids that the refinery already has, we borrow them from the refinery, we estify the soup. Then we could solubilize it, and this works very nicely. And when you do this, you can co-process it, and you can shoot it in the hydrotreater. But it's a very complicated process, and it's very expensive. And it's this part that is expensive. We used isopropanol and nickel catalyst here. And even if nickel is a cheap metal and isopropanol is not the worst solvent, it still kills the economics of this. So then we had Christian, who is now the CTO of the company, but he was a postdoc in my group at this time. He said, can't we just solubilize the lignin and send it to the refinery and see what they say? And I said, no, it's not a good idea. We will clog their reactors and they will not be happy with us. And he said, okay, but maybe we should try anyway. And we were a little bit desperate at this time because we had promised the refinery that we would solve their problem. So we said, okay, let's do this. We just estified the lignin, and we sent it to the refinery, and we sent also the one that we had depolymerized. And they didn't see any difference. So it worked. Actually, it didn't work directly, but we had to grade the catalyst bed, so we had very non-reactive catalyst in the top layer of the catalyst. Then we could get it to work. So this was published 4 years ago, and it's still the state of the art. There's another group that has published continuous hydroprocessing of lignin. They used RCF oils, and they ran for 8 hours. This is 300 hours. And you can see, like, the first 6 days, the catalyst bed is not in steady state yet. So it takes 6 days to stabilize the feed over the bed, and then you have pretty stable operation. Since then, we have ran in 100 bars for 300 hours, and then been able to lower the pressure to 80 bars and run another 300 hours. We have also started at 80 bars and gone down to 60 bars. So why do we want to run it in different pressures? Well, if you have a refinery, they will have different injection points for a possible feed. So hydrocracking is maybe 120 bars. The hydrotreating of vacuum gas oils is maybe 100. And then you have 80 in the light gas oils, and then also maybe 60 in the naphthas. So something that is important when you work with all biofeeds is that you shoot off these oxygens, and that costs considerable amounts of hydrogen. So for 1 ton of lignin, you need about 70 kilograms of hydrogen. And then we have in the feed, we also have fatty acids and some acetates. So if you want to sell a biofuel, you have to have at least 70% greenhouse gas reductions. So if a refinery gets a tall oil or a fatty acid that has maybe 75% reduction, then they cannot hydrotreat it with steam reformed hydrogen from natural gas, because then they will go below the point where they can call it the biofuel. So some refineries now are implementing, for example, electrolysis to generate green hydrogen. But this is not the case with lignin. So lignin generates methane, and this methane can be reformed to generate hydrogen. And even in the softwood that only has 1 methoxy group, you can almost get back all the hydrogen that you need. If you have a hardwood, you get a surplus. So this is a bad, not pedagogical picture, but what I want to show is for 1 lignin that you put in, you get about 0.55 biofuel out. The theoretical maximum is 60%, so you get 5% that go up in gases and also in heavies. So if you look at the techno-economics of this, you have a higher investment cost, and depending on where you sell, and also you have a 55% yield, and depending on where you sell this, in the US or in Europe, you'll get different return of investment. So anyway, you increase the revenue by a factor of 3 to an order of magnitude. But, yeah, okay, and this is the CAP. We founded it in 2013. We have made considerable investments. We have been rather active in IPR, and unfortunately, we closed our business in Sweden, and this is something that is maybe a little bit specific with this business. It's a regulated business, right? So if a politician says that we will not have biofuels, then you don't have any business. And this is what happened in Sweden. But we have non-disclosed partners in Europe, and we also have disclosed in US Comstock. And we are very, very amazed by the Americans, because they have done the trip that we did in Europe in 15 years. They've done that in less than 2 years. So they have raised capital to build the first plant already. So when we were doing this, Alex here, he asked the question, do we only have to make fuels? Because right here that this is a liquid, but it's a liquid at some point. Depending on the ratio you have between the fatty acid and the lignin, and also what fatty acid you have, this liquid is maybe a liquid at 80 or 100 degrees. So it's more a thermoplastic material. So the mechanical properties of the material itself is very poor. So we thought, okay, maybe we can blend it into other thermoplastics. So we did it in PE, PP, and PLA. And you see, it works to do it. You can do it. But you can also see that the mechanical properties are linearly correlated. So if you have 50% lignin, you lose 50% of the mechanical properties. So it works, but it doesn't work that well. So in 2015, and we sold it in 2018. So I don't have any obligations to this company anymore, but they're doing pretty good. They are commercializing these internet shopping bags. But thermoplastics are a little bit problematic. I mean, 10 years ago, the KPIs were degradability and bio components in the plastic. But since the 5 last years, it's all about recycling. And then if you have mixed feeds, it is more challenging. So we tried a lot of fatty acids because different refineries have different fatty acids. And usually it is a liquid at some point, and then it gets a solid at some point. But when we did linoleic acid, it became a solid, and we could not heat it up. So we looked at what was happening, and we get the esterification first, but then you have these 2 olefins that are epoxidized in air. And this was what happened. We didn't understand it at the time. And then the lignin can act as a nucleophile to attack these sites, and then you get the cross-linking. And then you don't have a thermoplast anymore, you have a thermoset. And the first applications, we looked at veneers, but we had problems because the mechanical properties were good, but they were not excellent. And also, everyone that has worked with the Kraft lignin knows it has a lovely Finnish sauna smell to it. But not everyone appreciates this, unfortunately. So that led us to find an outdoor application, and we aimed at traffic signs. So we were developing the recipe for these permanent signs, and we were very close to meet specifications, but we were just under these. So then we had to go back to the lab and develop again new chemistry. And then we found a better cross-linker, a better recipe, and we found such a good formulation that we could go for temporary signs that are made of ABS plastics at the moment. And we can reach 70 megapascal flexural strain in these without having any reinforcement. The lignin content is above 50%. And when we fixed the chemistry for the mechanical property, we also got rid of the odor. So now we're looking for indoor applications. And we can also, it is compatible, we can make it compatible with both type of fibers, so we can also increase the mechanical strength to above 100. So now we are at the level of ABS, for example. So we founded this in 2018, and I would say last 2 years it's picked up, and it's mostly because of this ligniset, the thermoset that we have developed. So the most important slide. No, not the most important slide. The most important slide comes after this. Just to show the techno-economics. Here we have 100% yield. This is wrong. The one should be there, so it's a little bit higher, but it's a very low capex and opex to this. That yield is 100, and the revenue is much higher. And so here you can get a very good return of investment. Now comes the most important slide. So Alex, Pierre, and Davide, Christian, and Joachim, they all developed our recipe in our lab. First in the academic group, and then in the company. Johan and Christopher, they went over to Lignin Industries, but they have also contributed a lot, especially to the thermoplastics. Marcus is the one that is doing the hydroprocessing in our group. So these guys are amazing. They are going so fast that we cannot keep track of them. Södra has been supporting us during our whole year journey, and I don't want to take, I hope that we have inspired them to start producing lignin next year. So they will open up lignin outtake from 2027, I think. And then these people are working with the traffic signs. These are from the refining from the beginning. And then I want to thank the funders for supporting us. And then, of course, I want to thank you after the conference dinner for your kind attention. Thank you.
All right. Thank you, Nina, for the introduction. Good morning, everyone. It's a pleasure to be here today. So first of all, I would like to thank the FinnCERES organizing committee for the invitation to present. Where is the presentation?
Yeah, forward. Yeah.
Okay, all right. So my name is Mar Borrega. I'm working as a principal scientist and project manager at VTT. And today I'll be telling you some of the work that we are doing regarding the valorization of softwood bark. So I'll start with this slide, which sort of summarizes the message that I want to convey today, and is especially addressed to forest companies. If you have bark, don't burn it. Let's do something together and develop bio-based products and at the same time reduce CO2 emissions. So I'll show you some examples of bio-based products that you can make out of bark. But first of all, I'll start from the beginning. So why are we working with bark? Well, basically for two reasons. One, it's a side stream. I also, as the previous presenter said, I don't agree that it's a waste. It has a value, but it's a side stream. It's a residue from the forest industries, which is generated when debarking the wood logs. The second reason is that it's really abundant. So it's one of the lignocellulosic residues which are most abundant in Finland and in the EU. Only in Finland, if we consider the softwood bark, availability is between 2 and 3 million tons per year. That in EU would be around 12-15 million tons. But what is happening nowadays with bark? So it's combusted in the mills to produce energy. And it has a value, as I said. It's energy value, which is relatively low. But one of the main issues nowadays is also the emission of CO2. If we consider these 2.5 million tons of softwood bark available in Finland being incinerated, that will release something like 5 million tons of CO2 per year. Is that a lot? Well, if we look at total CO2 emissions in Finland in 2023, including land use and forest sector, we have about 53 million tons. So only the incineration of bark is roughly 10% of the total CO2 emissions. So it's not an insignificant number, it's quite high. So if we don't burn it, what can we do with it? And why should we work with it? Well, if we look at the composition of the two main softwood species, spruce and pine, well, there are carbohydrates, quite many, and then there are polyphenols, quite a lot of polyphenols. By polyphenols, I mean lignin mostly, and then condensed tannins. There are also the phenolic substances in minor presence, but condensed tannins are typically the main compound of interest in bark, and that is because lignin is, you can get it from wood, but condensed tannins are specific to softwood bark. If we don't go to other hardwoods from Southern Europe and the tropics. But in the Nordics, there are no condensed tannins in the wood. So how can we extract these condensed tannins from bark? Yes, we can. Typically, this is done with a water extraction. Water extraction is a simple process, and it works. But at VTT, we have now been working for several years on developing an alkaline extraction. And why is that? Because we've seen that, for example, in the case of spruce bark, it varies a little bit depending on the conditions we get. Typically, we get 25% of polyphenols. If we compare this to a water extraction, we get about 5%. So it's 5 times more yield, and this should improve the economics significantly. So this is our valorization concept that we're working on at VTT. So we start with our softwood bark, we do the alkaline extraction, we recover the polyphenols that we will use in some applications, but one of the benefits also of this alkaline extraction is that the extraction power so it's quite an efficient process. So then you get a bark residue which is enriched in cellulose, and that also enhances the possibility to valorize the bark residue. So if we follow this concept, basically we get around two-thirds of the initial bark that we could valorize in different applications. And now I'll show you some applications where you can use the polyphenols as well as the bark residue. Let's start with polyphenol. Something we looked at a few years ago was to use them as surfactants. So polyphenols, meaning mostly the condensed tannins, maybe some lignin. Typically also they have some carbohydrates attached, so those are amphiphilic molecules, and you can use them as surfactants. We compare them to for example, some commercial surfactants, also to lignin, and we saw that actually these polyphenols from the alkaline extraction had quite a good performance, similar to a commercial biosurfactant and better than lignin, for instance. Something that should be taken into account is that if you are planning to use these polyphenols as surfactant, the formulation should be so that it's at a neutral or at a basic pH, because at the pH of around 6, when we go below this pH, then the solubility starts decreasing dramatically, so then it starts precipitating. So it should be neutral to basic pH. Another thing that we've been doing within the context of the bark build project, which just ended this year, is to use these condensed tannins as preservatives for wood protection. Basically to substitute synthetic preservatives that are commonly used and which are very toxic and harmful to human health and environment. So in this case, we work with radiata pine. We impregnated those wood blocks and we subjected them to decay resistance test, both brown and white rot fungi. What we could see was that if we use, for example, the bark extracts directly without recovering the polyphenol, so just after the alkaline extractions, those actually had a really good effect in preventing the growth of fungi, but this effect was possibly masked by the presence of sodium hydroxide there. If we recover the polyphenols and then we use that in the formulation together with a cross-linker to prevent leaching, we had a reduction in fungal decay by more than 50%, which is good, still far from commercial preservatives, but something to continue developing and really avoid the use of these really toxic preservatives. Now, another potential use is to make resins, and resins, for example, for wood coatings, and or to use them as binders. Here we work again with the alkaline extract that we got after extraction of spruce bark, and together with a cross-linker and some additives, we made a resin. The resin contained about 30% of bark polyphenols, total bio-based content of 80%, and then this we could coat it on some wood, but we could also use it as a binder for biochar, and the biochar was from spruce bark. The idea here was to develop functional coatings that, for example, could be used to absorb VOCs and improve air quality indoors. So this worked actually pretty well. It was tested for absorbance of formaldehyde, and the coatings show quite a good absorbance of formaldehyde. Most of the absorbance came from the biochar as a VOC absorbent, but actually the coating had also an effect, especially when you were increasing the thickness. So this is also a potential application. Of course, you can use it to bind any other type of particles as well. Now, this is one of the main applications we are currently looking at. This is done within the context of a Superbark project. It's a European project funded by Circular Biobase Europe. And we're developing adhesives for wood panels. We're working actually, we are 4 partners working in this specific development, and each partner has uses a different formulation, different chemistries, and we are targeting either plywood, particle board, or MDF. This example here is from VTT. So we work with our polyphenols. We use a cross-linker, like for example, Hexamin, and now we have been optimizing the formulation, we have been optimizing the pressing parameters, and we are reaching the target, the shear strength target that we want to reach, and then we are planning to transition into testing the adhesives in the actual plywood manufacturing. So we will also test different cross-linkers, and as I said, there are different formulations being developed. So here, one of the main challenges or ambitions is to develop a resin that is at least 95% bio-based content. So this is quite an ambitious target, and the idea is to replace fossil-based solutions like phenol formaldehyde, urea formaldehyde, and all these adhesives which are, again, toxic and harmful to human health and environment. Now, for the bark residues, what could you do with it? So, as I said before, when we do this alkaline extraction, this is quite powerful in extracting components from the bark. So you end up with a bark residue which is highly enriched in carbohydrate. So about 2/3 is enriched in carbohydrates. So why not use it in pulping? So that's what we did. We took these bark residues and we mixed them with wood chips, and then we did some craft cooking, typical craft cooking, and what we could see is that for every 1% of bark residue that we were adding, we were getting around 0.6, 0.8 of unbleached pulp yield. So this means that you would be able to increase, a pulp mill would be able to increase the pulp output without increasing the consumption of wood, and quite significantly. Of course, you're limited by the amount of wood, of bark that there is in the tree, but if you consider a 10%, that's a very good increase in pulp yield. Then we did the bleaching to see whether the addition of bark residues would have any issue. No issues. You could bleach the pulp to full brightness. Then we did some sheets. No issue with the mechanical properties or physical properties. So this could be a really good application for the bark residues. Another one is to use it as a sugar source. So it's enriched in sugars. Why not do hydrolysis and use it for the sugar route? So this works as well. You can hydrolyze about 80% of the sugars with a high enzyme dosage. If you reduce this dosage, you will still hydrolyze around 65%. So this is also quite a good application for it. And then the 2 last ones I want to show you are also developed within the Superbark project, related to the use of making nanocellulose. So we have been using this bark residue, fibrillating it. It fibrillates rather nicely. It produces this nice chocolate-looking nanocellulose up here. And then you can make, for example, films. You can also tune, you can do some bleaching if you want to the bark residue to adjust the content of residual polyphenols. You will end up, for example, having films having different colors. And we have been testing the barrier properties, and some of them, especially when you remove polyphenols, they start having very good barrier properties. Finally, also related to CNF is to the development of wood coatings, and this is done by one of our partners, Holzforschung, Austria. So they use this CNF in a paste form. They use it as a filler in coatings, in wood coatings. And they have been adding this, this is actually an error, it's around 1%, not 10%. So they have been, by adding about 1% of this unbleached bark-based nanocellulose, you can improve, for example, the scratch and abrasion resistance of, in this case, it was plywood. So, takeaway message, this was quite condensed. So I just want you to remember that if you have bark and you would like to do something else than burning it, or you are working in the development of bio-based products and you think that bark could be interesting, we will be very happy to collaborate with you, so please reach out. And I would like to acknowledge all of my colleagues at VTT, also some other colleagues in other organizations. Here you can see a list of organizations, companies, and research institutes that have been supporting us in the different projects, as well as the funding organizations. And yeah, that's all. Thank you very much for your attention.
Thank you for the introduction. And thank you for listening. I am going to quickly tell a little bit about one application for lignin. And basically it's to offer a solution for what we can do with lignin in the membrane application. And for this example, we are going to be extracting the lignin using deep eutectic solvent, and then have one application where it's used in conventional membrane process, and then we take it a step further where we are going to try to do something that is bio-based. And then finally, I'm going to present a new idea where it's basically just lignin as your material for membrane. So I guess it's very nice to mention that apart from the fact that there's a lot of lignin available because of this growth in the bio-based field, one thing to note is that lignin as a material is full of a lot of this kind of functional group and makes it a very good material for any kind of application. You just have to use a little bit of imagination, and then you can, of course, do a lot of things with lignin. One of those would be to introduce things like antioxidant properties or antibacterial properties into material. And when I talk about membrane, I will tell why it's very important. However, the aim is to see if we can actually take advantage of this material, lignin, and combine it to membrane without compromising the things that we want from our membrane. So good performance in terms of selectivity and separation. And then further on, since we have lignin, we're thinking that why not produce something that is completely bio-based or biodegradable. And then we can reduce the problems of this end-of-life membrane being stored somewhere. So I tell a story about how you make membranes. So basically, when we make a membrane, we take a polymer. It could be bio-based, it could be petroleum-based, and then we add some kind of additives, and we find a very good solvent. We make a solution, and these additives to the membrane is basically to help improve the functionality of the membrane. You can add, depending on what you want, you can add antioxidant properties, you can add pore-forming activity there, you can put some kind of cleaning agent, depending on what you want. So you make this kind of solution, you put it in an answer, so you use a casting knife, and then you can control the thickness of your membrane on a substrate. And your substrate could be glass or some kind of cloth, polyethylene or whatever. Add it in a water to remove the solvent, because typically water is a good anti-solvent, so you create precipitation of your polymer with the additive or without the additives. And then, of course, you end up with some kind of a membrane, and typically if you are going to make a flat sheet membrane, it's going to go this way. You spread it out, and then you have membrane, and then you can use it for your separation. And now the additives could be whatever, and many cases, one of the big challenges with membrane is that after a while it gets fouled and then nothing goes through it, especially when treating wastewater. It could be biofoulant. And then adding some antioxidant there would help in this kind of process. And then you have this kind of thick polymer that probably is hydrophobic and nothing goes through it. So you tend to add something to improve that, to allow things to go through it. For that, we decided to use lignin, and we wanted to extract our lignin using deep eutectic solvents, which are a class of green solvents that is based solely on the combination of an hydrogen bond donor and an hydrogen bond acceptor. Based on this, you have two high melting compounds, and then with the right combination, you depress the melting point to a point where you have a solution. And the good thing about it, unlike ionic liquid, is that it's very easy to prepare, and the purity of your DES depends solely on the purity of your starting material. So if you start with two pure compounds, you end up with a DES, and then you don't need any kind of further purification at the end. So for this case, and then you have all those nice properties that comes with solvents like this, like very selective separation and things like that. Here we chose choline chloride as our hydrogen bond acceptor and lactic acid as hydrogen bond donor. And then we do the process in that we make the mixture, have it cool down, take wood chips, put it in it, and then for this we separate this kind of undissolved material, which is a cellulose-rich material, and then in solution we have lignin and our solvents. We remove some of the solvent we used in washing, which was acetone water mixture. So we remove the acetone mainly, and then we can induce precipitation by adding some more water. And what we end up is lignin. Well, we dry it, and then we have this lignin, and we decided to continue. And now for the first case, we are making a conventional membrane using polyethylene sulfone as the main polymer for our lignin, for the membrane. And it looks something like this. And then we can, as additive, use lignin. And then we were able to combine different amount of lignin to this. What we saw is that we were able to have a very compatible material, so the lignin stays in the system and not leaking out. And then we noticed some increase in the antioxidant and the antibacterial activity of the membrane. And so what it means is that we were able to combine lignin to this polymer, and then it stays there, and then it gives us what we want. But further on, it's in terms of the performance of the membrane, we noticed that, for instance, the contact angle reduced. What this means is that the membrane becomes more hydrophilic, so water goes through it. It improves the porosity of the membrane. So, of course, that also means that we can get water through it. And then, in this case, we are not influencing negatively their rejection, so the material behavior, the membrane behavior. So it was able, to separate ethyl glycol 35 kD just the way the reference membrane would be. However, it had better, in terms of the hydrophilicity, it was better. And so in this example, using this kind of petroleum-based material, what we can do is that we can control the behavior of the membrane, the performance of the membrane, by controlling the amount of lignin that we have there. In this example, we stopped at 1% of lignin. But then when we talk about using this kind of bio-based material. An example here was using polylactic acid. Of course, one could use something like cellulose acetate as your bio-based material. The same thing, we saw this good compatibility. And in this example, we were able to increase the contact angle, so making it more hydrophilic up to 75% without seriously affecting the way the membrane behaves. And so by increasing the amount of lignin, we could play with the trade-off between the behavior of the membrane in terms of separation of your compound and in terms of the permeability. And so you can, of course, drop the amount of lignin you have there, and then you can improve the behavior of the membrane in both ways. We saw that there was an increase in the charge on the surface of the membrane. This also helps in the separation, depending on what you are trying to separate. But all in all, in this example, what we were able to do was that we produced an ultrafiltration membrane where lignin is about 8% in the matrix of the membrane, without really detrimentally affecting how the membrane behaves. And this is one case where we have used a bio-based material. So we offer this kind of controlled way to control the way the membrane behaves when we have used lignin as both as additive there in the membrane, and then this can work for the conventional methods of making membrane, and also when we think about something like a bio-based membrane. The main control or the main trade-off would be the amount of lignin you have in your system. And but with this, we were thinking that why not take it one step further? And finally, what we did was to produce a membrane, and this is something that we are still working on, that is purely made from this lignin material. So, of course, it was deep eutectic-based lignin, and it is having like 3.5 kilodalton as the cutoff, and it's quite good in, it's quite hydrophilic, and then it's rather tight, and so we can actually control, in this case, this kind of material, especially in application. By making it even tighter, we can take it further for even in gas separation. And so we offer this way as one way that we can use this lignin, depending on where you extract your lignin from, to make membranes for different kind of separation application. And then with that, I say thank you for your attention.
Thank you so much. And today, I have been given the task to start a session. Yesterday, I was here opening the World Circular Economy session. It was pretty tough because that's serious and I was reading. But today, I get to talk about my own work, and that's pretty much fine, exciting, and I'm still nervous anyways. But the title that we came up with, me and some people from my research group, is pretty tough: Secondary Materials Circularity Beyond Recycling. After we suggested the title, we started working on it. It's like, what did we do? Why did we complicate our lives? We could have done something simpler, but here is what we came up with. What I want you to leave here today is with this provocative thought, that I will start with a theory, we'll talk a little bit about how it's done in practice, and then a little bit about how we touched on research. But I think you all, if you're here, you already think about circularity and you probably apply it, but maybe there's a little bit more that we could inspire to today's talk. It is quite boring. That's why I'm starting with theory, so you have a lot of text there. The idea is to remind us that the circular economy is an economic system. A lot of the time we interchange circular economy and circularity, but just I want to remind you of the word economy in there. It's an economic model. It's a system. It's about materials. It's about waste. And it talks about a lot of interesting keywords. One of them is recycling. That is the topic of today's session. And you all have seen this, right? This butterfly diagram. I guess. It's it's like, okay, they have seen it. Should I show it? No, maybe. But the blue side is the finite materials, the green side, renewables, and then the idea is that we shorten as much as possible these feedback loops. The priority is the shorter ones rather than the long ones. And it's pretty, when we think about the bioeconomy, it's pretty obvious that we're probably in the green side, right? Easy, not complicated. My students always say, why are you showing this one? It's so simple. But then when we think about textiles, which is the topic of today, a lot of the time we have mixed things, right? It's very hard to get a textile that's 100% bio-based. We can have our cotton shirt, but most of what we're wearing today, it's a mix of different products. And today we're talking about recycling, and that's one of the complications that we have in that sense. So I'm kind of talking about the simple things from theory, again. And then this drawing was something that I drew in the first year of my PhD. I was very proud of it because it was my bioeconomy value chain. I was doing supply chain analysis and lignin work. And it looks nice, circular. But now with the research group, we start looking at circularity on what it is and how it manifests through policy. On, off, back. Okay, good. We start thinking, oh my God, each one in this value chain thinks in a different way, uses different ways of assessing these keywords, and depending on who they're talking to, they may also talk in different ways. And I was only seeing the picture. If I point there, you see. No. I was only thinking about the biorefinery. That was my topic. So I was thinking about how do I recover it? How do I increase yield? How do I, close the loops over here? But then I was never thinking about what issues might I create here or here, and not even end of life was part of the topic at the time. And now as researchers, we need to think about all of those things, either by ourselves or collaborating with others. So then we go to textiles. Then that beautiful, simple, circular value chain I showed gets much more complicated. And I chose this picture on purpose. It's from our dear friend Kitsini Maki from Arts and Design in Aalto. And here she shows very well that it's different. It comes from different feedstocks. For instance, the natural fibers is the focus here. But it happens in different places. It generates different types of wastes. And it goes through a lot of different stakeholders in the value chain. So I think you already know that. But it's a quite complicated, one of the most difficult value chains to turn circular. That perhaps is not news, and I want to emphasize that there is a lot of pre-consumer textile and post-consumer textile waste being generated over time. It doesn't matter if it's coming from fossil or bio-based, this waste is generated over time. And then to give a little bit more of a taste of what is generated, this is a very simplified diagram, and I think the author is only talking about clothing here, but just to have an idea, so we have most of it coming from plastic, for example. When we are making the clothing, we are losing something during the production, and then we use the clothes several times, we wash it, we generate microplastics, and then lots of it is landfilled. We try to recycle, or mostly downcycle, if there is a little number 2 there, and the number 2 refers to lower value applications in this case, and then very little is actually closed loop, and we have recently been able to bring some new feedstocks, maybe agri-based that we heard from Caio yesterday about this food waste feedstocks and other types of feedstocks. So from other value chains into the textile value chains. But it's not a good picture, we know that. So far, value chain, bio-based, circularity, textiles. Then this picture sounds pessimistic, but researchers, we should be optimistic. So here is one opportunity to bring waste from other value chains into this picture. We have an opportunity to reduce landfill, the recycling picture, which is so important, but perhaps upcycling and other things to be improved. And we have a huge opportunity to keep the loop within the manufacturing system or to improve the use of pre-consumer textile waste as well. And these R's, have you seen them? Raise your hand. This way, the 9 R's. okay, not a lot of people. I was expecting everybody was an expert on this thing. And you know, the idea here, and people might disagree with the hierarchy presented here, but the idea here is that if we are on top, here we are more circular. As we go down, we are closer to the linear economy, so we are less circular. And don't get me wrong, I'm all about recycled. It has to be done. It's what we have to do right now. But you know, the idea is that we try to rethink, reuse, and reduce as much as we can. And maybe I'm biased, maybe no, I am, towards biorefinery concepts. And in there, we try to reuse, recycle as much as we can within the process. So I like, when I pitch about biorefineries, I like to say a lot about what we do over there on the top. And then I was thinking, okay, for this topic about recycling, what examples could we bring? Then my students have visited Rester in Finland. Do you know them? Yes, a lot of people saying yes, many not moving. It's not coming from them, it's our opinion from public available information. So we look, okay, they are doing something quite interesting in Finland. So they are a good example. So they seem to be driven by the EPR and other regulations. There might have been some infrastructure. They have built their facility where there was municipality incentives. We heard yesterday that that's something important for innovators, where they go where there is some kind of incentive. And then we talked about, okay, what are they doing here in Finland about textile recycling? And then apparently they are making mostly this non-woven. They are working with companies to reduce this supply chain risk, where there's some of these companies like Lindstrom, they are able to actually bring the textile directly back to Rester rather than then collecting from many different places, apparently. And they use this mechanical process to recycle. And then we were thinking about what could be done better. So they prefer natural fibers. And of course, these problems of collection and creating waste applies to everybody. But I think that one of the issues is like there are limitations in terms of what fiber they can process, and I think they tend to downcycle. They tend to be using this in this like non-woven applications. It's great. We have to do that, but could we do better? And then we were talking in this 3 hours in a room with 4 of my PhDs, and we were saying, what can we do better? And then everybody came out, and you have seen this sentence, I'm pretty sure, in papers, in journals, in the Times. I actually should have put a picture of the Times, that we cannot recycle our way out of the waste problem. We have to recycle. It's inevitable, like Vida, she's sitting over there, she said that sentence over here. But there are other strategies. And then I said, but I need to talk about this in this event. And what are we doing in our research group that is better? What can we show to the audience? And then we have these, this name, right, that we need to honor, Sustainable Bioproducts Innovations. And the word there is sustainability. Circularity is one part of what we have to address. So before I give you the examples of our work, I just want to say how we approach things. We are trying, at least, to approach circularity. And I love the bubbles, and my research group made a joke of that because we have bubbles everywhere. So we have the environmental bubble, the techno-economic bubbles, the circularity. Have the strong sustainability in a way as an overarching is not shown here, otherwise it would be too many bubbles. But we conduct these life cycle assessments, techno-economic analysis, social life cycle assessments, life cycle costing. I am an engineering, so process design, getting the mass and energy balances there. And then, we have to address circularity because that's how things are manifesting. So the idea is that we develop some types of key performance indicators that would help accelerate the innovations that have been presented yesterday, today, a lot of these solutions. So how do we make them to become a reality faster? By taking into consideration these things early on. I have 2 examples from how we are working on this. One of them is this EU project called Self-Fill. And it's a bit of a messy figure, but one interesting thing that I want you to take a look at, the reason for the orange and green is because the main feedstock, orange peels and wood from the lyocell process. So in here, perhaps, I hope, that we are, when I showed you that slide that have this kind of Sankey diagram where we have waste materials coming from other value chains. This is the idea with the orange peels being pulped and coming into the lyocell process. And we are trying to figure out something that's quite challenging for our partners, is that we have to go all the way not only to the staple fiber but to the e-yarn, and then the yarn becomes a piece of a shoe or a car seat, which is then tested, which then comes back. So we are going to go through that loop several times until we figure out how much orange peel, how much post-consumer textile waste, how much can we mix and how should we mix. And then we do not want to downcycle. We want to actually add value. We want to go to the toughest applications in this project. And I am doing the easiest part, and you can search more about it. There's a lot going on. I'm not the easiest part. Of course, as supervisor, we do the easiest part. But the researchers, Maria Livia and Tuba that you see there, Maria Livia is the LCA, Tuba is the techno-economic analysis. We are responsible for creating, at the end of 5 years, this is an innovation action. So we have 5 years to create this blueprint. What are the steps that need to be taken for this innovation to go from TRL 5 to 7 to commercial? So, and we are working together with Arts, with Kirsten and Nimaki, and they are doing all of these consumer surveys, the social LCA, helping us in that part. And all of the partners, of course. And this is a nice picture of the orange after they have grinded it to make the pulp from Sicily in Italy, that we visited the company there, the startup, which is sitting next to a food producer company. And many other orange-based ingredients that are produced there, and this is just the waste that goes to the startup. Then another great example, and it's actually a FinnCERES example, is the work in collaboration with Monika and Sahar. Here, one of our PhD students, she has such a big title, right? Value chain approach, circular bio-based products. But in simple ways, we are working on lignin, which is my dear friend, and I'm a lignin person. So Sahar has developed from Monika's group this amazing coating that has a lot of properties, as you can see there, the antibacterial, which you, anti-staining, FS-free, all of those amazing things. Our main goal is the economic analysis at the moment, but it keeps me bugging me that this amazing coating should be put into kids' clothes. And because my kid always stains everything, and I cannot give the clothes to my friends who are having kids because most of them look awful. I just waste them. So I was thinking we should do some type of life cycle assessment, looking at this coating and the potential of extending their life. It's a dream. It came out last week. I haven't even discussed with Sahar or with Monika yet. But I think we need to think about bio-based products in the future. Like, what can we do that's not only 100% bio-based, but can do better in textiles? It's going to take a lot of time. It's going to take 15, 20 years. But then I get to these take-home messages is that, so going back to the beginning of the talk, that the textile value chain is one of the toughest to turn circular. I hope that you agree with me. And circularity doesn't mean sustainability. It's part of it. It might support it. That we know we cannot not only rely on policy. Yes, it's a driver, but we need everybody else to take an action, that the idea of the orange fibers, that the waste of the orange fibers can become a feedstock for the lyocell. It's not easy, it's expensive, what we found so far, very expensive, and maybe even higher footprint if we don't scale up. But we should, as researchers, aim high. I mean, we should think about these bio-based solutions, the example of Sahar's work and the coating. Can we have this fully bio-based extended life textile? And can we measure this early on to kind of guide research towards that? So that's the presentation for today. Thank you.
There we go. So, hello everybody. My name is Kirsi Roine. I'm the Chief Customer Officer at Infinite Fiber, which is a chemical recycler of cotton. I always start with one thing. Every single second, there's a truckload of old clothes going to incineration. Every second. We just heard from Luana that recycling is mandatory. And what we are doing is just that. Our mission is to turn textiles circularity to everyday reality. Our solution is called Infina. Infina is a fiber that is fully made out of old clothes. So it's a fully circular solution. And our philosophy is that nothing new needs to be grown. Infinity Fiber was founded in 2016. As you can see, we are quite well backed with investors, and we have multi-year agreements with brand partners. So there is a lot of support from this value chain. Also, we were talking earlier about the value chain, how complex it is. It's not only about the brands that we need everybody to come together. And what we are doing now is that with 15 people, we are scaling up. And next thing is a commercial facility. So, how we do this? We start collecting the materials that is cotton heavy. So it could be, for example, your old jeans. That comes to our system, and what is done first is that it needs to be shredded. All the hard parts like patterns are removed. We pulp the material to remove the polyesters, we remove the colors, ending up only with the cellulose that lives in cotton. Now next, and that's the uniqueness of our process, is called carbamation. What we do, we force the cellulose to react with urea. That creates a cellulose carbamate powder. And that powder is activated in a way that it can be dissolved into the cellulose liquid. And now, when we are in a liquid stage, cellulose is dissolved. So if there's, for example, elastane, we can filter it out. It doesn't dissolve. So we are actually solving the blended materials problem also. And when we crystallize the cellulose back, then we get Infina, the new fiber, that can go to yarn spinners, fabric manufacturers, and finally into the garments. Here are some of the properties of Infina. The kind of uniqueness of Infina is to how it feels. When you create Infina, it still looks and feels like cotton. It's supply chain ready, so it can be thrown into the yarn manufacturer, and they can use any spinning method to do yarns. So in that perspective, value chain is already there with us doing the circularity. Also, it's biodegradable because it's fully cellulosic. And it saves water. Because if you compare, for example, cotton growing, it's a little bit of a different number. 2,700 liters of water for 1 kilo of cotton is needed. For us, it's a fraction of that. Then, what I promised to talk about today is when you scale up, you need to have market ready, and then the regularity environment needs to be supporting. Now when we go to the demand side, we have calculated that these kind of fibers, in 2030, there's a need for 4.5 million tons. So we don't need the regulatory environment to be supporting us. There's already a huge demand without that. But actually, brand sustainability commitments, that regulation that is evolving, consumer preferences, and investor net zero commitments are also the drivers. So now, when we're talking about the regulation that's supportive, those three alone, brand sustainability commitments, consumer preference, and net zero commitments, those can really drive the circularity of textiles. Then, this looks very busy, but so is the regulatory environment in EU today. So there is the kind of like an overall thing called EU Green Deal. And under that is a circular economy action. And in that, there is a sustainable textile strategy. And what that means for textiles is that there will be regulations on shipments, how the waste can be traveling around the world. For example, there's a ban for delivering old clothes outside of the EU. So we start piling up with the textile waste. Then there is a big talk ongoing about where is the end of waste point. When the garment that is come to the circular system is collected, it's waste. But when it goes, for example, to reuse, is it waste or is that already a new product? So that kind of conversations are ongoing in the EU. Then there is a big thing called Eco-Design for Sustainable Products Regulation. I'm talking about ESPR. What that means is that it will be regulated how the materials are designed, how your future T-shirt is designed. It needs to have a certain aspects ready. For example, there is ongoing talk that it needs to have a recycling content. That is also one part of the market drivers. If every single cloth needs to have a recycling content in the future, we need recycled materials. It's also very important that when you design for circularity, that you think about the end life. And that's what is happening at the moment. You need to be, for example, thinking that, let's take a kind of like ice cream bar. If you're selecting that I'm making a cotton T-shirt, what would be the kind of like would I take a strawberry sauce, or what I would do? I can take a little bit of polyester to make the seams to last better. I can also let's take a print, but not anymore. You need to be thinking that those already are actually somewhat harmful for the recycling. You need to be thinking what to select. And that's one of the very important aspects in ESPR. Also, clothes needs to be durable. The biggest sustainable action is to make clothes durable. So if, for example, you are having Gucci luggage, and you use that for years and years, and then you give it to your son, and he uses that years and years, and it has a 30 years lifespan. It's the most sustainable product because it has been used so long. So that's one of the important aspects in there. And with that also comes a digital product passport. So us as a consumers know what we are purchasing, which is important for us to understand that what is in that product that I'm buying. I can make a sustainable choice. And digital product passport is allowing us to do that. If you think about that from the market perspective and the recycler perspective, for us it would be a dream that there is in every single garment, there is a label that tells what is actually in there. Because then it would be much easier to put that into recycling. We know that, okay, this is a 100% cotton T-shirt. Let's go. That would be perfect. Then there is also a Green Claims Directive. You can't communicate without a proof. So that's a market driver, I would say, for the certificators. Because we need certificates in every single thing to prove what we are communicating. And then overall, there is, of course, Corporate Sustainability Reporting Directive. There was Omnibus just kind of like easing it up, and seems that there's other one coming that might be affecting to the Sustainable Textile Strategy timelines. But let's see about that. So what Infinna does is that we are actually helping brands to meet their sustainability targets and all those regulations, making them compliant. So it's, from our perspective, the collaboration between us and the brand partners is so important that we are designing something that they can use easily, they can communicate easily, and with what they can be compliant to the evolving regulation. Also, we need to talk about something that is called recyclable garment. When you're talking about recyclable garment, Infina is one solution that can really allow it to be fully circular, because you can recycle Infina again with a little bit more cotton in the stream also. So that's why we are telling brands always that if you blend Infina, blend it with cotton, because cotton polymerization level is higher than Infina's, and that's supporting the recycling. You can see there some of the environmental impacts that Infina is creating. Of course, when you are producing and doing chemical recycling, it's very important that you select the right ways to do that. For example, if we would be producing in China and using coal, I think that the numbers could be quite different. Then, getting to the end, regulation benefits for capacity scale-up. Regulation is supporting innovation. There is evolving extended producer responsibility, and through that we know that materials are circulating and they are collected. That's important. It's enabling also the long-term collaboration models and really reducing the risk that there is no feedstock available for us. And if we think about what is the biggest benefit, is that there will be incentives in the future. And that is one of the drivers. Because Infina is going to be high-priced. It's not only because it's very expensive to do that. It's because there is a market imbalance for supply and demand. And also, then the incentives can help the brands to take them into their collections. Thank you.
Thank you very much for the kind introductions. I'm really privileged to be able to be the last speaker in this wonderful event. I also had the possibility to pitch yesterday, so now I'll take this opportunity to provide a bit more background information on the principles of what we do. Pretty much continuing with the topic that Kirsi was speaking on, just with a slightly different technical spin. So I'll give you some background, a couple of examples on our work during the past few years, and then something to conclude. So really, Kirsi was already nicely putting this forward, so really it is a global challenge. If we think about the textile manufacturing industry, it's a huge market and it's growing fast. During the last 20 years, we've seen that the amount or the volume of produced fibers and the number of sold items has doubled. At the same time, our consumption has changed. So essentially, we're buying more clothes and we're using the clothes that we buy less. And this obviously presents an environmental problem because we then end up creating and generating more and more waste. I mentioned this figure yesterday, so the average European now generates 15 kilos of waste, textile waste every year, and this could increase to 20 kilos by 2030. Textile recycling per se, back to fibers, is still really just starting off, so the majority is incinerated or landfilled, and according to some estimates, less than 1% is currently being recycled back to fibers. Now, Kirsi mentioned some of the regulatory background. This has been acknowledged by the European Union, and we now have regulation that mandates that EU member states organize separate collection of household textile waste since January this year In addition, there's these other regulations that Kirsi mapped. And really, textile recycling, the way we recycle fibers, depends on fiber type. So provocatively, you could say that recycling at scale really requires that we are able to build efficient textile sorting systems. These systems are currently breaking ground in the textile field. The majority of them are based on near-infrared sensors. These are non-invasive reflectance measurements where we actually measure the light in respect to a white standard from the sample. As a rule of thumb, you could say that NII is quick to measure but complicated to interpret. So you always have this connection to some kind of mathematical tool, whether it's machine learning, chemometrics, but still some kind of modeling activity. Molar absorptivity in the NIR increases as a function of increasing wavelength, which gives this characteristic shape for these spectra. Essentially, we measure oval tones and combinations from the mid-infrared, unharmonic ones, which means that we often have a larger atom coupled to a smaller atom. For example, oxygen and hydrogen, or carbon and hydrogen, which is also one of the reasons why it's well suited to cellulose and its derivatives. The idea is in principle to get material fingerprints that we can then use for developing classification or regression algorithms for different purposes. Here's a couple of practical technology examples. This spectral engines is a VTT spin-off from the beginning of the 2000s. They make handheld sensors that you could essentially couple to a mobile phone, and then you could have some predictive algorithm in the cloud. This is a pilot facility run by now LUT, Lappeenranta University of Technology, in the Lahti campus. So basically you have a conveyor belt, and then you have a spectrometer, a traditional spectrometer, and then the fabrics pass under the spectrometer, and then you have pressurized air that then moves them into different baskets based on the measurement and the results of the algorithm. This is an industrial example run by Sysav, a waste management company in southern Sweden in Malmö. This facility was designed by Stadler and Tomra, and they produce these automated bales of sorted textile waste and then sell, I think, mainly the cotton-rich textile waste then to their customers in Sweden. What we do is that we work with hyperspectral cameras where we're actually able to determine a spectrum in each pixel in the image. This gives us some advantages that I'm going to show you later. Here we have a principle of, an example of what that means in practice. So we have a fabric where you can see some kind of a shape. If you take an image with your mobile phone, it's a visible image, so you can only see that everything's white. But when we take an image of this with a hyperspectral camera, we can differentiate that the part in the middle, the heart-shaped figure, is most likely chemically different than the surrounding fabric. Then if we interpret the differences in the wavelengths, we can make an educated guess that the red areas most likely contain polyester, and then the surrounding fabric is some kind of cellulosic fiber, cotton, viscose, or lyocell. And then what's interesting actually in this example is that this part where you've ended or stitched together the fabric here, they've used both fibers, both polyester and cellulosic fibers, and this color nicely aligns between these two extremes. So you can take images and derive conclusions or hypotheses on the chemical composition of the material. We started our work in the FinnCERES project 2019, and this was one of the first things that we did. We wanted to see whether we could accurately estimate the composition of polyester cellulose blends. This is important because polyester now covers approximately 2/3 of all textile fibers produced, and the amount of these blends in clothing is increasing all the time because they have some favorable properties. Like Kirsi mentioned, polyester is actually a residue in chemical recycling of cellulosic fibers. What we showed that not only can you identify the separate fiber types, but you can accurately predict the composition of these blends based on NIR images and latent variable regression models. We were working with a range from 0 to 100% polyester, and we had test set prediction errors which were less than 5%. So the method seems to be very accurate. Here you see some image examples. So you have a lyocell polyester blend in the upper row, and then you have a polyester sample in the lower row. You have a visual image here, and then you have images of the predictions based on the measurement and the model. So you can see that for the polyester, we predict 100% polyester, and then for the blend, we can see the chemical differences within the sample. What's interesting here is that the polyester parts are not actually 100% polyester because you have a full cellulose layer on the bottom side of the fabric. So not all the incident radiation is absorbed right in the surface, but you get sort of a guesstimate of also the cross-section of the sample. This is some of our newer stuff. This is what a lot of textile companies are interested in, detecting elastane, and often small amounts of elastane, especially in cotton. Widely used to provide stretch for fabrics, for example, jeans, and often, especially with cotton, you have very small amounts. So we're talking a couple of percentages only. It's difficult to detect, even in the lab, and then difficult to remove and causes problems both for chemical and mechanical recycling. And we've shown that we can accurately classify materials, cotton materials that contain elastane, even in the range of 2 to 6% using this method. And then this is what most chemical recyclers are interested in, degree of polymerization. Kirsi also touched upon this quickly, because degree of polymerization decreases with mechanical and chemical degradation, but it governs the viscoelastic properties of dissolved fibers. And these properties recyclers need to monitor and control to be able to efficiently spin fibers in chemical recycling. We've created patented technology to do this based on average NIR image spectra, which we can then couple with classification or regression models to estimate intrinsic viscosity. I give a figure here. We estimate that with 30 kilotons a year and 8,000 hours a year, and if you sell your fibers 3 euros per kilo, we could save more than 10,000 euros per hour by avoiding process disturbances if we compare monitoring intrinsic viscosity with traditional lab methods. Now, we used a feature extraction and a discriminant classifier in this work. And when we analyzed the wavelengths responsible for the discrimination, we could see that we noticed differences in cellulose crystallinity, and potentially differences in some oxygen-hydrogen bands in the material. And we made this hypothesis that maybe it's the more amorphous parts in the cellulose fibers that get decomposed upon degradation. And then we did some additional analysis, and we could actually sort of confirm that materials that had lower intrinsic viscosity, lower degree of polymerization, had higher relative crystallinity in the fibers. Essentially, we don't fully know what we are measuring, which is one of the problems when working with NIR. And this is why our development with the FinnCERES book is very exciting. So we're now continuing developing this method together with methods developed by Paavo Penttilä and Antti Paajanen, using X-ray scattering and computational simulations to study fiber degradation in the lab. I mentioned yesterday that we have 3 main objectives. We want to try to understand the fundamental mechanisms of fiber degradation in cellulosic textiles. And then second, we want to simulate NIR spectra to really provide an understanding of what it is that we are measuring in the fibers that enables us to discriminate degree of polymerization, and then also to achieve TRL4 by lab scale validation with a prediction error lower than 50 milliliters per gram expressed in intrinsic viscosity. And really we believe that in the future we might have possibility to extend this methodology also to the broader field of cellulose modification, so not only limiting it for textiles. Okay, so something to take home. Textile recycling depends on fiber type and properties, and really a recycling system at scale, we're gonna need efficient automated sorting systems. And chemical recycling not only requires information on fiber type, but also on more detailed polymer properties to monitor and control the recycling process. Spectral imaging provides some advantages compared to traditional spectrometers. So we have a spectrum in every single pixel of an image, which provides a sampling advantage and enables us to really differentiate more minute chemical details. I liked what Kirsi said in the end of her presentation, that we talk about a circular economy of textiles, but this system doesn't really exist yet. There's no circular economy of textiles yet. So what really us for developers, I think the important question is, what kind of information are we going to need in building such a system? Before I quit, I just want to thank some of our funders, so flagships from the Academy, both the Finnish Center for AI and the AI-driven design of materials highlight, and also obviously FinnCERES, and then the Phoenix project where we started this work back in 2019. Thank you very much.